Hello, everyone, and welcome to the 11th iteration of CoqPL. This might, in fact, be the last iteration of CoqPL with this name. I guess we'll find out next year. My name is Ben Delaware, and together with Catherine Stark, I'm the co-chairing this year's iteration of the workshop. So that's it. Without further ado, we have some really exciting talks planned today, starting off with Enrico Tassi, who is a researcher at the INRIA Sophia Antonopoulos and a member of the Coq development team. He did his PhD at the University of Bologna, where he worked on the design and implementation of Matita, math components team on odd order theorem. Sorry, I'm reading Catherine's notes here. So, LP is a high, right, so today he's going to be talking about LP. LP is a high-level programming language designed to implement new commands and tactics for the ROC theorem prover, which is what he's going to be talking about. Good. Followed by, and that'll be followed by two talks, one by Joshua Cohen and one by Thibault.
Okay. Thanks for the introduction. So yes, the plan is to talk about this language LP2 that allows you to write new commands and tactics for ROC. I will give you a soft introduction of the language. I will give a demo on how it is integrated in the system, and I will compare it with the alternatives. But before that, I want to start talking about something that makes me proud. I selected 4 projects that use LP, and I will advertise them, but also pinpoint which are the key features of LP that these projects rely on. The first one is Hierarchy Builder. It's a domain-specific language to describe a hierarchy of interfaces and organize a library around it. Just to help you read the snippet here, hbmixin is the name of the command that is implemented in LP, while the record declaration is an argument to the command, and the command is registering this piece of interface into its database. Then later one can assemble these pieces of interfaces into the nodes of the hierarchy that we call structures, as I do here. And then one is in business. He can, for example, postulate a monoid M, a point in the monoid, and try to develop his abstract theory of monoids. In this case, maybe not writing a property which is false, but that's not the point. The point is that a lot of boilerplate is generated automatically behind the scenes using the extensive LP APIs. The HB generates modules, and then it generates for each node in the hierarchy coercions between them. It instruments the unifier of Coq to compare them properly. It sets implicit arguments, abbreviations, all the kind of boring things you don't want to think about. And given that it has a first-class representation of the hierarchy, it can implement nice commands like there is one called how-to. You ask in the system, I have this type, I want to make it an inhabitant of that interface, which are the pieces that are missing, for example. Or you can draw the interface by generating a dot file that then you can display as you like. And what I really like about this project is that, about HB, is that when we port the mathematical components library to it, it kind of unlocked the growth of the algebraic hierarchy. The red line in the graph down there is the number of interfaces up to 2022, and the number was stagnant. It was really hard to add more interfaces. And the green line is when we started to port it to Hierarchy Builder. Now most of them are defined using this tool. And they are growing, especially the order theory part of the mathematical components library got way more complete after that because they could add so easily more interfaces and make their theory grow. Another project I want to mention is Stroke. Implements a form of gradualized univalent parametricity. It allows you to transfer, let's say, proofs, statements from one type to another one. And it works roughly like so. You define a relation between two types, in this case, the very simple example, natural numbers and binary natural numbers. And then you also put in relation the symbols, the constructors for the natural numbers, and this successor function for the binary ones. And then you are facing a goal on the binary numbers, but you want to go back to the world of unary numbers where you have more proof tools. Well, you just call the tool, and you are back into the realm of nuts, and then you can use a theorem about natural numbers. The key features of LP that it uses is that the translation is implemented with rules, and when the user registers this relation, is just adding rules to an existing program. It is extending it. And moreover, when it does a pass over the term to transport to the other world, it collects constraints, another feature of LP. And then at the very end, it looks at the constraint, it checks which are the axioms that one needs in order for the parametricity translation, for the univariant parametricity translation to work. Most of the times you don't need univariance, for example. Okay, so even if the translation works beautifully everywhere, if you have univariance, you don't really need it all the times. And this is what ROC does. Derive is a framework for synthesizing code automatically out of data types declaration. It is actually the first application written in CoqLP, and I presented it in this very workshop in Los Angeles quite some time ago. To help you read what happens here, derive is the name of the command. This is an argument, which is, well, just a record declaration. And these attributes are options for the command. I'm saying, please put all the derived notions inside a module and synthesize for me an equality test and and the laws of lenses. So here you can see that he created a module, he put the type in it, and he also synthesized an equality test. As you expect, it says, I can compare two boxes if you give me a way to compare the contents. He won't ask you a way to compare the tag because it's a natural number, so there's already an equality test for it. Lenses in the Coq community are sometimes called record update syntax. Lens comes from Haskell, I think. The idea is that you have a lens, in this case underscore tag, to focus updates on a field of the record. And it also synthesized for me this little theorem, among others, that says that if I have a box R and I want to perform two updates with X and Y, well, if I first write Y there and then X, then what comes out of it is X, so the second one wins. And there are a few derivations written there and some more in the wild, proprietary code. Apparently a company likes to extend it and run it, but not all code is public. And the last project I want to mention is Algebra Tactics. You're probably familiar with the ring tactic for Coq, and you probably like it. I like it too, but in the mathematical component library for a long time, it just didn't work. And the reason is that ring is a reflexive tactic. So there is a meta program that looks at the syntax of your goal, recognizes operations of a ring, the types of ring, and then it translates them into a data type. And then there is a program, proof correct, that runs, that really implements the ring simplification on it. Unfortunately, in MathComp, recognizing ring operation is not so obvious because there is a hierarchy of structures. So maybe you have a field, but the operation is from a ring, so there is a projection. So the work of the reification phase needs to be a bit more clever. And in particular, this tactic makes use of the possibility LP gives you to call the unification of Coq in a very surgical way. And what makes me happy is that all in all, the performance of the reification procedure that Katsvik obtained is pretty good. So they have an example in their repository with a 500 lines polynomial. And the new ring tactic, let's say, solves it in dozens of seconds, something like that. And the reification phase is not the dominating factor. Okay? So even if it's smarter, if it does unification here and there, it's still acceptable. Okay? I wouldn't say it's blazing fast. Of course, it's lower than the standard one because it does more work, but it's still acceptable. Okay. Now what does it look like? So from a programming language perspective, LP is a constraint logic programming language, and it is a dialect of both Lambda Prolog and CHR. CHR means constraint handling rules. Maybe you never heard of CHR, it's not very important. You surely heard of Prolog, and when people hear Prolog, they say backtracking, this is the interesting part of the language. While no, I don't care, you almost never need it. What really matters to me is that the code of ELP or Lambda Prolog is organized into rules. And it is really the life motive of my talk. I will try to point out where it really plays an important role. These rules are applied following a pattern. And more importantly, these rules can be added both statically to a program or dynamically at runtime. Rules look like this. There is a head, and it really means if the goal looks like this, well, solve it by generating these two smaller goals. The languages are from the 90s, so their syntax looks a bit vintage to me today, but I couldn't find a better one, so I kept it. And there is a convention that variables, parameters of rules are capital letters, and the lambda abstraction is written this way. So this is lambda x point t. Okay. So the hello world example of Lambda Prolog and also ELP, even if I will try to push it a bit further, is a type checker for simply typed lambda calculus. This is the syntax you use to declare an algebraic data type. The type of terms has two constructors, app and lam. App packs together two terms, y in higher order abstract syntax style. The lam node packs a function of ELP to represent the binding of a variable in an expression. Okay, and for the types, I just have the arrow constructor. Okay, so this is how you would write in this syntax the first function, lambda x, lambda y x. Okay, now the type checker is a predicate that relates a term to a type. There is this input-output annotations there. I will come back to them in a moment. For now, ignore it. And then the type checker reads pretty much as on paper. So if we have to check the application of a head to an argument, well, the head better have as type an arrow type from S to T, and the argument better have type S. What is more interesting is the rule for lambda abstraction. Remember that here f is a function, okay, of LP. So we assign to a lambda an arrow type from S to T. Now we have to synthesize T looking at the body of f. So what do? We postulate a fresh symbol, let's say a constant C. We add to our program a rule that this C has type S, okay? And then we do the recursive call on the body of the function to recover the type T. And by passing the fresh constant to the function, we are replacing the bound variable by this constant, okay? So I will run the program on this little example. So, of course, the second rule is the one that applies. So type first is going to be arrow, okay? There will be a fresh symbol C that replaces the bound variable x. So this is the bound variable x. It is replaced by C. This is the type we synthesized so far. We are recursing over the target of this type. And we have added here to our program an extra rule that says that C has type S0 in this case. And we repeat the thing. Now our original type has grown. It is almost correct. It says there just is not correlating, it's not relating the input, the first input to the target type yet, but there is still a goal to be solved. We are asking which is the type of C, and this type should be T1. But here in my program, C has type S0, so T1 and the S0 must be the same. So in the end, the type that is computed for us is alpha or beta or alpha. That is what we expected to find. So this was all known in the 90s. This is pretty standard Lambda Prolog. But if I want to use this language in the outer layers of ROC, I need to be able to manipulate open terms, terms that are not complete, that contain holes. Okay. EVARs in the ROC slang, okay? So this is a kind of term I want to feed to my program, okay? And here it fails. Actually, if you know a little Prolog, you wonder why it fails instead of diverging, okay? Because Prolog would consume some input, then find a term which is not rigid and start to generate all possible terms. Well, not really all of them, but while here it fails immediately because of this annotation here. Input really means use these patterns to match the goal against these patterns instead of unify the goal against these patterns. So it's really you really look at them as OCaml pattern matching, really, rather than unification if they are flagged as input. So here the program stops, but I don't want it to stop. So here it comes constraints. I add a rule that says if my input happens to be a variable, a unification variable that I call E, well, I generate a constraint of the same shape. So in a way, I suspend the current goal. And I schedule its resumption as soon as E materializes, okay, as soon as the input materializes. So now this succeeds and gives me two constraints, that the head has type ROST and the argument has type S. Now what happens if later in the program someone assigns H, for example, to the identity function, okay? We expect S and T to become the same because the identity function is type alpha or alpha, of course, and this to propagate there. And this is exactly what happens if we chain the first goal with another one, okay? And what makes me think that all of this makes sense is that I obtain the same result as if I had plugged the identity function right in, okay? So I'm just changing the order in which the computation really takes place, but it doesn't change the result. So I'm happier. But not completely. For example, if I try to type check self-application, this type system should reject it, okay? But I end up in this situation, which is not something I want. And this is where constraint handling rules come into play. I can add this rule that says if the constraint store contains two type assignment, two typing constraints on the same X for T1 and T2, that this bar means remove the second one and put back an equation. So try to unify them. And in this case, they don't unify, so the program fails. Okay? And that's pretty much all about the language. Now, questions, maybe? Now, what makes it useful? Sure.
Oh, yeah, now it's on. If you could clarify the status of these UVARs, so how, I guess maybe you talk about it in the next slide, how they're integrated into Coq, or is it just a separate constant UVAR, or?
I will say a bit more about that, but
because it seems like
just a
similar
keyword.
to app and lam.
It's just a keyword. It says it's a special case.
Okay, it's a special keyword in
some Prolog implementation, you would have a specific language to describe delays. Say delay when. I don't have this language, but I have a bit of a hackish syntax to do the same. It gives me more freedom of how to compute what to suspend on, because I have my own language to describe it rather than a built-in one. That's it. So now, when it is integrated in Coq, of course, you have a description of the terms of Coq in higher order abstract syntax. I won't show it to you because you usually don't need to know all the details for little demos, because you have a system of quotation and anti-quotations. For example, this is an API to print a message. And these double curly braces jump from the world of LP to the world of Coq. So inside here, you have a term written using the Coq syntax parsed with the Coq parser. Okay? And this LP colon curly brace goes back to the world of the syntax tree of LP, where I build an application. And maybe this term construction should talk about, because we will see it. Global is the coercion from references to global notions to terms. Okay, it's global constants that are available in the environment of Coq. There is a notion of databases of rules that can be extended programmatically. This will be used in the demo. And there is an extensive API, for example, and it's very tiny to read, but there is a way to ask the Coq environment all he knows about an inductive data type, like the list of constructors, their types, how many parameters, if they are uniform, is it inductive, co-inductive, all these kind of things, and that's it. So maybe the main point of this slide is to show you that the entry point to all the documentation is the GitHub page, and that here there's a menu. As you can see, there is a documentation section with tutorials and proof of concept, so that you you don't necessarily need to start from a blank page. You have something that looks like what you want to do, and then you play with it and you make it grow to your needs. So now I would like to make a little demo. Great. So I will implement a little proof transfer tool, very basic, very stupid, but it will allow me to show you many features of the language. So imagine that I have a predicate in prop that says is even, as you can expect, and an implementation of it as a Boolean test, okay? And imagine that someone proved that they are strictly related. So reflect really means if and only if. So if this Boolean test evaluates to true if and only if the number is even, okay? And I also have something for connectives. These two Boolean tests and their Boolean conjunction evaluates to true if and only if P and Q holds, assuming that big P and small p are in if and only if relation, and the same for Q, okay? The last piece of infrastructure I need is a limT that says, well, it's projecting one of the directions of the if and only if the proposition and the Boolean are related and the Boolean is true, then the proposition holds, okay? And now I have this goal in prop, and I want to automate the writing of this ugly line that allows me to switch to the world of Booleans, where I can compute and use reflection in a way to solve my goal. This ugly proof term I wrote by hand as a fixed part, which is a limT. We are going backward to the Booleans. This whole here is the subproof that is generated, and what really the work of the tactic will be is to synthesize this term looking at the type. So how do I do that? Let me maybe put it here. To bool. Okay, so the entry point for tactics is called solve. It takes a goal. A goal has many arguments, but what really matters to us is the type we have to inhabit, okay? And the idea of solve is that it takes a goal and generates a list of sub-goals. This is how the entry point is supposed to work. So we want to, at the end of the day, we want to refine, it's called a limT of a certain proof that I will synthesize, and that's it. So this is the scaffoldings, and now I will write some code to synthesize this P out of tie, okay? Let me call it this TB. So it takes a term to a term, and my invariant is that TB P R is that R is going to have type in Coq reflect P of something, okay? So if I find is even of some n, well, oops, the term I want to generate is even P of the same number. This is the first rule I put in my program. While if something for conjunction, a bit of, if it looks like P and Q, well, I use the NP, and then I need to pass to it a proof for P and a proof for Q, okay? Let's call it this, PP, PQ, and then I do the recursive calls. P will give me the proof of P, and the recursive call to Q will give me the proof for Q. That's pretty much it. So now if I remove this, and I didn't do mistakes, the new tactic does the same thing as before, okay? So maybe it's okay, but maybe not. What I don't like about what I wrote right now is that if I'm adding a new lemma, like for Boolean disjunction, whatever, I have to come back here and fix my code, okay? But I want my code to continue, evolve, and work as the library grows, okay? Now everything is on my screen, so maybe it doesn't look like a real problem, but So how do we do that? First, we declare one of these things that I call databases, tubull.db, and this database will contain rules for one predicate, this one. Sure, just let me finish the sentence. Okay.
How is the two-bool tactic wired up with, like, you have an LP tactic two-bool, and then there's a next command, which that's a completely separate command, right? But somehow they are connected to make the two-bool tactic
All right, sorry.
wired up with the solve thing?
Commands and tactics are made of many pieces of code that you accumulate together. So this means, let's begin the definition of the two-bool tactic. This will accumulate on top of it some fixed code, okay? And then you can repeat this many times. There is no end, really, okay? They are open-ended, the program. So I didn't put a delimiter to say this is the end of the definition, because the definition is meant to grow anyway. I don't know if it makes sense.
Okay, yeah, it makes sense, thanks.
Shredder, sorry.
Just a quick follow-up to that question. So you could say two-bool, accumulate rules, then you could have another tactic, accumulate rules, and then could you switch back to two-bool and add?
Yeah, sure, you can do that, but the more civilized way to do that is via databases that I will just demo. Maybe Brigitte has a question. I don't know if it was the same. Okay. So the idea is that I have this entity, a database that can gather rules for the TB predicate and can be extended programmatically. Now my tactic won't have this code anymore. Okay, I just commented because I need it. My tactic will accumulate the DB. Okay, and of course now it fails because the database is empty. There are no rules. Okay. Now what I want to write is a program that takes stuff like this. I want to implement a command that does this: register NP and register, how was it called? Even P. Okay, this program will take these Coq terms, compute their type, use the type to synthesize rules and add the rules to the database. Okay. It will essentially synthesize the syntax that I wrote here and put them in the database. Oh, sorry. Now we are in another world, so another way to make comments. The main difference is that when you programmatically describe a rule, you need to make all quantification explicit. So this rule really should look like this for all n, while this one should really look like rule PQ, PP, PQ, and stuff like that. Okay. But other than that, are really the same rules. So let's do this command. Register. Okay, so this time it will be a bit more tough, but okay, we will do it. So the entry point for comments called main. It will takes a list of arguments, in this case a string. Then there is an API to locate the string and get a global reference, like a pointer to the environment of Rock. Then all global references have a type. That's pretty much what Rock is about. And now we will compile this type and the global reference in order to obtain a new rule. And then I will add my rule to the two-bool database, and the rule is going to be like this, okay? A bit of a mouthful. There are many options I don't want to even talk about, but the idea is that I synthesize some code and I add it to the database, okay? Now, my function to synthesize this code will be fueled by the type. Okay. The proof and the invariant is that the second argument, global, the second argument is a term of type, the first argument. Okay, this will be the invariant during the recursion, and I will need an accumulator to remember the recursive calls. So let me write it here. It's a term, another term with the invariant I just said, a list of recursive call, list of propositions, a list of predicates, let's say, and it will generate the proposition. So when the type I'm looking at is reflect of some S, and I have a proof of this reflect, and I have something to do, well, the rule I want to synthesize will be tuple of the proposition that is in the first reflect argument, and its proof will be R, and proviso that I do everything that was left to be done. Now, the type of the theorem could contain an arrow with a reflect on the left, an hypothesis. So if it looks like reflect S arrow tie, okay, I have an R, I have a to-do. This time I will have to synthesize the theorem as an argument, so I need to quantify it here. So the rule I'm going to generate will start with something like this, okay? I will make it explicit. Now, in higher order APSA syntax tradition, whenever you want to move under a binder, you write a pi. Okay, so let's assume I have a variable for that. I have to do my recursive call on tie. Okay. Now if this has type arrow, the recursive call is on tie, so the conclusion of the arrow. So I need to apply this R to the term that plays the role of the abstraction, so H. I have to remember it will be a recursive call, okay? So I have to remember, this is how you write cons. I'll have to remember to transform S into a Boolean, and the proof is going to be H, okay? And then I do the recursive call on, I will synthesize the body of the rule. And the last case is when the type of the theorem is for all x tie, and in this case the type depends on x. This is the syntax how you say that. There is an R, there is a to-do, and even this time I have to do something like this. So I do as I did before. In order to do my recursion this time, tie depends on x, so I need to pass something to x, to it as well. My proof term has to be applied to x as well. I will keep the same to-do list because it's not a recursive call. So, for example, here I had for all p, q, etc. These are not recursive calls, while these are. So this is why I'm not touching my to-do list. And this should be it. Now, I lied to Ralph a little more. No, it's not. I didn't lie. It's just that I need a command to say that register is available without writing LP register. Okay, so, and this usually goes at the end of the definition of a command. But the command is not. Is still open-ended because it accumulates a database. Okay, so a bit like the tag. So it's not really ending the definition, it's just making it available. And now if you go back to our to our proof, we have the same tactic as before that works, but we populated the database of rules programmatically. Okay. Now this is a bit of a mouthful. If you're used to higher order APSA syntax, it's kind of trivial, but if you're not, I understand you. You may look at me with eyes, okay? But believe me, you get easily acquainted to it.
The two underscores in clause, I was sort of expecting that you'd have to specify what those are on line 53. No, when you call accumulate on line 53.
Yes. You mean this underscore?
No, 53.
53, sorry. Well, this is, in all my APIs, arguments with a default value can be passed as an underscore. So this is where the rule should be put. This the name of the rule. This is an unnamed rule. And this is a grafting point because you can say, I want to graph this rule before that or after that. And by default, it goes to the end of the database. It's just a syntax for default arguments. Sure.
So this is really cool. I have two questions. So one is, so you might be in a subgoal that has some variables introduced because you're proving something for all. So currently in your lemma, it's like ground, essentially, right? So how do you make sure that, for example, the natural number then, because that might live in some kind of other context where you already have like some bound variable, because you're proving something about for all natural numbers, for example, right? How do you make sure that you respect that binding?
Respect the binding,
or like basically you have not only, I mean, your numbers are not going to be closed. So you wrote, I think, in one of your rules that you need to write the pi explicitly, and the pi was :nat, and it's not.
I'm not so sure I will answer your question, but
okay.
I will add something. So, for example, there is I try very hard to give you the illusion that, sorry, that the programming language handles for you the context, as in the proof context, and EVAR maps, so the type and value assignment to unification variables. So here I moved inside a term, okay, using an eigenvariable, okay, a variable that is bound by the context of LP, of lambda prolog, without losing some information. For example, this could be nat, okay? And there is a convention that whenever you want to do this term traversal properly, you add to the context of the programming language something like this. Well, this I really don't care. Yes. So in this way, the variable really corresponds to a Coq one, and deep inside the term, I know its type, and that's it.
Right. Okay. I have another question.
Okay.
So I mean, when you do this compile, if I understand correctly, you're compiling lemmas also, right? Is that correct?
So this is the name of the lemma. Oh, sorry, oops. This is the lemma, the proof of the lemma, and this is its type.
Yeah. So let's say you had early on in the example, you had this arithmetic solver, which where you might prove some properties about plus, like commutativity of plus or associativity of plus. Now, these are then rules in your logic program that can always be applied.
Right.
And so do you bound the search of the logic program? Because, I mean, when you call it as a tactic, right, it might go on forever.
Yeah, sure. No, there's no magic. So
okay. If it goes forever, it just goes forever.
So you can say LP bound steps 27,000 if you want, or you can be careful when you compile or write down by hand your rules so that it won't diverge. There is no magic. Okay. Maybe in the conclusion I will hint at something, but for now nothing is there. There is another question that maybe I should continue. I don't hear you. No, it doesn't.
Okay. Now it works. How are overlapping rules handled? Because, like, technically, it seems like the for all and the arrow before could overlap, like the last two of you compiled.
Well, this is a non-dependent product that it has on the left anyway, a reflect.
Yeah, but like if you like also the second one would match, right? Like if you have a reflect, you could also see.
Yeah, sure. okay, to answer you, this is how I would have written, but I didn't want to give. This means commit to this choice. Both match, you're right, but I want the first one to be selected, and if it's the case, when there is a reflect, I want the first one to be selected, but not the second. And you put a bang in. As a
Okay,
logic program.
but like the order also.
The
in which
order
you
matters.
put
It's
them
really
matters.
operational. It's
Yeah.
not. I'm.
Okay.
Thank you. So I really have to go back to the. Yeah. Well, okay, maybe I had questions. So that's good. So yep. In the abstract, in the short abstract, I compare it also to OCaml, LTAC1, and MTAC a little. Here I just picked the the two friends that are currently developed and actively developed. So all of them, all the languages have representation of Coq terms. The one of MetaCoq and LTAC2 is complete. They have all the details, even the details I don't like to see. For example, rock is coded in locally nameless, so you have variables by name and variables by the Brown indices, and you see this detail in LTAC2 and MetaCoq. In LP, you have higher order abstract syntax, so it's a bit more high level, but it's not complete because I didn't get to the implementation of mutual fixed point and mutual inductive types. This is a limitation for now. Support for bound variable is very easy. Once you get acquainted to higher order abstract syntax, it's very easy to manipulate bound variables. I mean, you have nothing to do. While LTAC2 and MetaCoq don't give you any support at the language level for that, of course you have quotations, so sometimes you can avoid writing the Brown indices, and in the case of LTAC2, quotations can be nested a bit like in LP, so you can get away with it more often, but still the complexity is there. All evers, they're fully transparent in LP. We never wrote an ever, we never threaded a substitution in the programs we wrote, so it's very high level. While in MetaCoq you have the node ever in the syntax tree, but no support for it yet. In LTAC2 is halfway because it's like ML, but it's implemented on top of the proof monad of the tactic monad of the proof engine of Rock. So this tactic monad has a state, and the state is the ever substitution, so you don't see that. You don't have to thread around a state, but still you have to use APIs to manipulate evers because they are not a primitive notion of the programming language. About the proof API, LTAC2 is clearly the most advanced one. From the very beginning, that was the objective, I think. MetaCoq doesn't have much there. You can fire type class resolution, and you can start a proof, but you cannot really do much. In LP, it's not too bad, but I'm not too happy either. There is a bridge to call LTAC1, which is a bit weak, in my opinion. It's very fine if you call a tactic that solves the goals. If you call a tactic that gives you back goals, you can do that, but it's a bit annoying to deal with it. I should really improve on that. Script in the vernacular, it's really where LP has has an advantage over the others. The only thing that is missing are the notations, the one with a long string. They are so ugly that I didn't get my hands on them. And I cannot start a proof. I cannot write a command that starts a proof obligation. Okay? Well, in MetaCoq is minimalistic. You can read and write from the logical environment, but that's pretty much it. You can start a proof otherwise. And where MetaCoq stands out is that you have a tool with a reasoning logic to reason about your program. That is Rock itself. That's so they didn't do artwork for that to work. It was already there. It was a smart choice. You have nothing like that for LP or LTAC2. I just wanted to mention Abella, which has a semantics for lambda prolog, and you can reason about lambda prolog. LP has much more than lambda prolog. It has these constraints, and you need a few non-logical features, so it's not usable out of the box. If someone wants to do it, not me, but if someone wants to do it, that's a start. And to conclude, so I wanted to say a few words about the role, I like the word extension language, and I like to think at LP as an extension language because it makes you think that from the very beginning, from the inception of the language, it is going to be used to extend a larger application. So you work from the very beginning to have a good FFI to exchange data with the host application, and this results in many APIs, and this is the strength of the language today. And you're allowed to use the language only when it is a good fit. Implementing the entire ROC in LP would be completely insane, but it proved to be, using LP for little extensions proved to be pretty handy. And the other point is that maybe we should look more into rule-based programming language. We use the rules to handle the context, the local context of our computation. The type checker I showed you didn't have a gamma. All the type checkers have a gamma, but this one didn't have because it's the programming language that gives you one. And we also extended the program with global rules that matched how the environment of an interactive prover grows. I mean, as the environment grows, you prove new definitions, new theorems, and you want to add rules so that your programs continue to work and take advantage of the new contents of the library and vice versa. And also the fact that the code unit is so simple, it makes it simpler to synthesize one. If we had to modify an entire ML program, we could do that. We would have to traverse a much more complex syntax artifact, and we could do it. While here it was trivial to just synthesize a little rule and add it. And for the future, so what I'm working on with the students is a type class solver written in this language. A bit like the compiler I wrote, but more sophisticated. And it goes hand in hand with something that we are going to do at the programming language level, a static analysis for determinacy, which would mean in Haskell slang, it would mean overlapping instances. We would like to detect them statically so that if you load two Coq libraries, you know if something is going wrong, if immediately two notions become a notion becomes ambiguous. And well, users want the features that I highlighted I don't have, so eventually I will add them. And the last thing we started working on, but we didn't finish, and this should answer a little the question of Brigitte before, is that we studied memorization techniques for logic programs, and that could make the language a bit more declarative. We hope to gain speed in type class search, but actually we don't have good examples because all the examples we could find are not very demanding after all. And also in our experiments, it takes more time to type check the proof you find, the instance you find, than to find it in LP. So we left this memorization track a bit on the side for now. And that's all I wanted to say. Thank you for inviting me, and thank you for contributing code.
Yeah, thank you. I think there is time for like 1 or 2 questions while the next speaker can already set up.
So for having done my fair share of logic programming,
So what we do right now is that we hook into the mechanism of Coq. So you still declare an instance, and we also compile it for our solver so that you can really compare the two solvers. And the preliminary experiment, I mean, we managed to compile TLC, STD++, a bit of Iris. Okay, so we didn't compile everything. And then what we see is that we are competitive in performance. Typically, we are slightly faster. Slightly, but the dominating factor is type checking the instance, as I was saying. So even if we get 10 times faster, it changes nothing. So we will have to dig deeper, I think.
and also quick question, can you add comments that add new instances?
Absolutely.
Yeah.
You can either write the instance rule by hand or write a command that synthesizes it as I did in the demo. Yeah, sure.
Okay.
So many questions. So what about if you have some kind of dependently typed data type you've defined? So since you're restricted to lambda prolog, right? So I mean, for example, you have here, you had early on this example of TM, right? You specified this, the lambda calculus essentially, but it is a reflection of what somebody maybe had written in Coq, right? So in Coq, maybe I would have written something that is already intrinsically typed. And then I want to reflect the rules, right, still into LP in order to work with it. Is there any way you're thinking about extensions to that? Because there's sort of this mismatch, right, of power.
Yes, but I think, okay, I didn't show it, but the syntax I wrote and the syntax I use for Coq, the one for Rock is a bit more deep embedded than that. So the type system of lambda prolog is too simplistic to match the one of Coq, so
right.
It's kind of loosely typed, the syntax tree you would get. So the extra constraints you get are in the type system of Coq. You can check them calling the type checker of Coq or do something on your own, but the language won't help you there.
Okay, all right,
Okay, thank you. Let's thank Enrico again.
Thank you.
And the next speaker will be Joshua Cohen, who will tell us about OCaml APIs in Coq.
Hello, everyone. Hi, I'm Josh. As I mentioned, I'm going to talk about a little technique for implementing OCaml APIs in Coq. So the typical way to write code that you want to write in Coq, verify, and then actually run is something like this. You handwrite some Galena function, like say list append, and then you call the extraction mechanism. You get some purely functional OCaml program. And then since you probably want your overall program to actually have some sort of effect, like reading or writing from a file or printing to the command line or something like that, you'll handwrite some additional OCaml code that will do the I/O operations or stateful operations that will call your purely functional extracted code. And then you can bundle and link everything together into a single executable at the end. But real programs are more complex than this. There's more than just sort of defining executables that you can run from the command line. And especially in the OCaml world, most programs are built around using and providing APIs. So if I were to write a slightly more realistic OCaml program, it would do something like this. If I want to append two lists, I'd probably call something, say, from the standard library. And maybe I want to combine multiple libraries. I want, say, some map from the core library. I want some graphs from OCaml graph, et cetera. And as I mentioned, sort of pretty much every large-scale OCaml library and program is built around these APIs, even ones that are designed to be run as executables. So we have both libraries like base and core and batteries whose only function is to basically provide these APIs. But then even, as I mentioned, these executable programs still have provide these APIs. So for instance, in the verification world, there's things like Frama-C, which is a verifier for C programs, or Y3, which is a like basically an intermediate language and a front end for SMT solvers, or Coq itself. All these programs are designed to be run as executables from the command line, but they also provide rich APIs for people to manipulate the kind of terms and formulas that you're using and to have more fine-grained control programmatically. And even things like, say, Z3, which aren't written in OCaml, might provide OCaml bindings for the same kind of reason. So we already know how we can reason about these kind of whole program executables, but how can we work with these APIs in Coq? So what we'd like to do is something like this, where we have an API implementation, and we can actually write down an implementation in Coq, extract to OCaml, and implement some existing interface. And this has the advantage where we can do things incrementally. We can look at parts of an API and identify the parts that are particularly, say, challenging to prove or interesting to reason about. We don't have to do everything at once. But we have a big constraint here, which is that we have to match the exact interface and the exact behavior that the OCaml client is expecting. And this turns out to be a big problem because, well, Coq or Galena, the functional language of Coq, and OCaml are very different languages. So for example, I show here a function from the Y3 API. As I mentioned, Y3 is this verification framework and this sort of front end for SMT solvers. And this is a function that creates an abstract function symbol declaration in their term language. And it's a pretty simple function. It has type L symbol arrow decal in OCaml, as you can see. But what is this function doing? Well, it does some error checks, and if there's some well-formedness check that fails, it'll throw an exception. And then it'll create the decal with that mkDecal function, which looks innocuous, but it's actually stateful. It's doing some hash consing. And of course, because we're in OCaml, none of this is reflected in the type. So if we're interpreting this L symbol arrow decal as some Coq type that we're trying to implement, this is a pure function that takes in an L symbol and must return a decal, when really the function that we want is a program that might throw an exception, it might give us a decal, but also modify some global state. So we can't really represent this using the same kind of Coq type. And there's a lot of features that fall into this category where we can't implement them or we can't implement them idiomatically with the same type in Coq. I'm going to focus in particular in this talk on exceptions in immutable state, but there are many others as well. And a key constraint that we have for sort of a particular application that I am using this for is that we want computable code in Coq. So we want to be able to do things like proof by reflection and to actually use like simplification and things like VM compute and so on this code to enable to take advantage of the nice computation capabilities that Coq has inside the proof assistant, which means we don't want to just like axiomatize all of the OCaml behavior. All right, so there's a lot of ways that people have thought about how to do this, and I'll talk about some of them at the end. Most of them tend to be quite heavyweight, and we sort of take the exact opposite approach. We take emphasizing this lightweight and pragmatic sort of methodology. And the key idea is to represent these features differently on both sides in Coq and in OCaml. And we link them together in a careful and principled way by modifying the extraction. And so we propose in this talk a sort of design principle for this idea. And if you are interested, I'll put a link at the end. There's a repository with some examples and a little library to enable programming with some common OCaml features. So let's look at an example of how this works. And let's look at the list.head function from the OCaml standard library. So this is a function that if you give a non-empty list, it'll give you the first element. If the list is empty, it will throw an exception. It has type tick a list arrow tick a, which of course is not representable in Coq. This would be very bad if we could write such a function. And but this is sort of the API that we want to implement. And the idea is that even though we want an OCaml implementation that uses exceptions, in Coq we're going to model this using an error monad. And so how does this work? Well, the first thing we do is we model exceptions in OCaml as a type in Coq. So we have this record error type, which just has a name and some arguments. And we can define specific models of exceptions, like say failure, which just at the bottom there, which just takes in our message. And then we define our monadic interface in Coq. So this is using the CoqXlib library, which has a whole bunch of monads and monadic interfaces. And so we can define our error monad as just the sum type that's either the exception model or a successful return. We can use from CoqXlib things like return and bind and throw an exception, which just gives the error case. You can also add things like try catch. For instance, this is just a simplification for the talk. And then the key part is that we want to extract this to an interface in OCaml that uses exceptions. And so we're going to erase this monadic interface when we extract. So our error MA, our error monad, just becomes type A. Our error type becomes exception, as we intended. And then we sort of push the types through all the monadic operations. So like return, for instance, in Coq has type A to error MA. And when we erase the monads, that's just A arrow A, which is the identity function, and so on. And then for specific exceptions like failure, we interpret this just as the OCaml exception failure. And now we can implement a function in Coq that lives in this error monad for the head. So we have a monadic return type. In the case where the list is empty, we have this throw, which again is just giving the error case in the monad. Otherwise, we return. And with this modified extraction, when we sort of turn the crank, we end up with the function in OCaml that we wanted with the type that we want and the behavior that we want. And so this kind of defines the recipe for doing this, where if we have some OCaml feature that we can't represent in Coq, we want to figure out a way we can model that kind of feature in Coq, identify some set of primitive operations to interact with this interface, and then map those primitive operations to OCaml. And as long as the Coq clients are only using the primitive operations to interact with that interface, I'll talk a little bit more about that at the end, then you get a lot of nice properties where your Coq code you can fully compute. It's similar to the code you would have written by hand. You can prove things about it as normal, and we don't have any axioms. There's no we're not sacrificing anything on the Coq side. Meanwhile, the OCaml code you get is computable. It has the right interface that we want, and clients can use the code. It doesn't have monads, for instance. All right, so mutable state is a little bit more complicated. We start with the same basic idea, where we're implementing it in Coq with a state monad and an OCaml with a mutable reference. And so again, we're going to extract this monadic interface. If we have our type state AB, where our state type is A and our return type is B, we just extract a B. We can sort of do the same kind of thing with return and bind. Now, because we're in a state monad, we have get and set, which we interpret as getting the value and setting the value of the mutable reference. And because we need to know which mutable reference we should actually be looking up, we encapsulate this in a module and make it so you can create a stateful computation in Coq or a mutable reference of any type. Now, the problem is that this isn't actually sound if you do this naively. And the problem is that the state monad is, at least morally speaking, a function. So we take in our old state and produce a new state and our return value, which means we have some way of applying this stateful computation to an initial state, which we can call run state. And if you imagine extracting this run state function, once we erase all the monads, in OCaml we would get this type like tick B, arrow tick A, arrow tick B. And the only reasonable thing we could do is just return the first argument, which is saying that we should ignore the initial state. And in OCaml, this makes sense because we already fixed the initial state. We created the mutable reference with some value. And if we were to instead say we want to run our whole computation with a different initial state, that's like going back in history and saying, well, if we had instead just instantiated this mutable reference with a different value and done everything all over again, here's what we would have gotten. And we can't do that. This is unsound. So a solution to this is, well, we can just fix the initial value. So our state module that I mentioned before is parameterized by this module type that includes both the type of the state we want, as well as the initial value or the default element. And then our run state function that we provide does not take in an initial state. It runs it starting from that fixed initial state. And in OCaml, we implement this by resetting the mutable reference to that initial value. So we can rerun the stateful computation as many times as we want in Coq or in OCaml. But either way, it's always going to start from the same value. And so, all right, we have these stateful computations and things like that. Well, how can we reason about this in Coq? So to show this, I gave an example in the repository of a small integer term API. So basically, we have some integer operations as well as variables, bindings, like let bindings and variables. This is inspired by the Y3 term API, but it's a much simpler and more general kind of case. And our variables and our bindings are abstract. So the way that this API works is the only way you can create these variables and bindings is with these functions here. And there's some global mutable counter that's generating fresh variable names every time you want to like substitute under a binder. So you can implement substitution statefully, but safely using this alpha conversion. And to prove things, like to prove the correctness of this substitution, we can use some ideas from the Hoare state monad from about 15 years ago, which you can basically think of as like a shallow embedding of Hoare-style reasoning in Coq about these kind of state monads. The exact definition on there is not like super important. The original paper kind of presents this in a dependently typed way, but we have like a non-dependently typed version, and we provide some useful sort of lemmas and ways to reason compositionally. And we can use this to prove the substitution function correct. So we have a theorem that says something like, if our input is well-formed, which means that all of our variables were created by the API, after we run this stateful computation of substitution, we end up with the result we expect, which is it's the same thing as just like adjusting the variable valuation appropriately with the substituted term. And all of this reasoning is like just basic Coq reasoning. We don't have any like deeply embedded program logics or anything like this. The state Hoare monad is really just like a nicer way to organize these kind of proofs, but you're really just reasoning in the core logic of Coq. Now, there's some limitations to this approach. I'll talk about a few of them. I won't have time to talk about all of them, I think. There's some issues with sort of scalability. So like for exceptions, for instance, we need a new, every time we want to model a different exception in OCaml, we need to define the model that in Coq and extract it to the corresponding exception. There's some Dune preprocessing. All this stuff I think could be automated, but right now there's a little bit of manual work in there. And of course, you have to trust the modified extraction, which is intended to be sort of small and something that you can easily kind of look at yourself and maybe not too controversial. But I'll talk a little bit more about that later. But yeah, that is more trust on the OCaml side. But the big limitation, the thing on the last bullet here, is due to limitations in the way that Coq handles opacity, we can't enforce this restriction that the Coq client is only using the interface. So for example, say you're in the error monad case, if you take your something in the error monad and you pattern match against it, that's perfectly fine in Coq because it's just a sum type. But in OCaml, now you're trying to pattern match on an exception and treating it as a sum type, which is going to cause type errors and all sorts of problems. And so unfortunately, this is a limitation at the moment. There may be some ways around it to thought about, but it's ultimately up to the user to make sure that they're using the interface correctly. And so there's a lot of work in this area about connecting imperative code and functional code and reasoning about imperative code and proof assistance from things like Why Not a while ago, about a framework, a sort of heavy-duty framework for embedding imperative programming reasoning inside Coq, which axiomatizes the stateful operations. Then there's more recent work like iTrees, where you can model impure code using a co-inductive monad, which means you can't necessarily compute everything in Coq from the co-induction. More interesting, these last three, so there's some similar work in CoqML, so you can implement some monadic functions to Hall and sort of synthesize stateful CoqML functions with some proofs, and some ideas from that would be useful for proving this correct if we had an appropriate semantics for OCaml. There's also formally verified defensive programming, which allows you to, in a safe way, to call OCaml code from Coq, and it uses this may return monad. So this would be useful to extend this with, like, you could have OCaml APIs where you implement part in Coq, but part of it also depends on some external OCaml code that you can verify the correctness of. And there's also VeriFFI, which was presented just a few days ago at POPL, which is a verified foreign function interface between Coq and C, so you can call C functions from Coq. And it solves this opacity issue that I mentioned by basically axiomatizing the external functions and providing some isomorphisms and rewrite rules. So some of these ideas I think could be used to extend this to sort of eliminate some of those limitations that I mentioned earlier. All right, so to wrap up, we present this approach that really aims to be lightweight, practical, to minimize the burden on the user, while being able to do a little bit better than like handwriting your OCaml APIs. And you get programs that are executable in both Coq and OCaml. They're reasonably idiomatic in both languages. They're usable by clients in both languages. And on the Coq side, we can reason about them in Coq, in ordinary Coq tactics and logic. As I mentioned, there's this repository available with some of these more involved examples. And yeah, thank you for listening. I'll now take questions.
We have time for some questions.
I'm wondering how you would approach verification of a pipeline like this. In particular, it seems like it would be intrinsically non-compositional in terms of, like, when you're adding things, you're redefining what xn means every time, right? And that would have problems for being able to say how, if you're using like two variations on this extraction, like, you know, you have two clients that have used your method, then having a verification, you would need some global view of everything in order to do a verification. I don't know, what are your opinions?
I'm not sure I completely understand. I mean, the things like the exception stuff, we only have to define those once, and to define the extraction commands once in some sort of like generic library, and you can just use that. If you have a particular like new exception that you want to add, like there was failure here, but you could add many more, those ones, like each time you have a new one, you have to add it, but you only have to add that. You don't have to like go and redefine everything. I'm not sure if I answered the question or.
So, well, I guess the way you originally presented it seemed like every client would be defining what exception.
Oh, no, sorry. This was just an overview of how the thing works, but really all the error monad stuff, the error monad interface is sort of generic. The only thing that you write each time by hand would be like the head function in the example.
I'm still a bit confused about this initial value thing with the state. Like, it seems if I run the computation once, that may change the state.
Yeah.
And then if I run it a second time, something has to reset it somewhere.
Yes.
Right? Where is that happening?
In OCaml, you think? Or
yeah, and which of these APIs is doing it? And if there's an API that can do that, why can't this just change set the initial state to whatever I'm setting it at without, like, if it can reset it to the original initial state, why can't I pick this every time I run the computation?
well, I mean, you could, but just by running a set before any other computation, before anything else you're doing, I guess. You could always set the state before anything else. So in this interface here, like this run state function is extracted. I didn't show what the extraction looks like, but it's extracted to something that basically returns nothing useful in OCaml, but just resets the value of that initial reference. And then the user is always free to set the state to whatever they want by just using the monadic set operation. But we just give this default initial state because otherwise, like in Coq, you could, like say you have some counter and you have an inker function and you could prove like, that inker starting point 1 equals inker 1 or whatever. But if you run inker twice in OCaml, that does like have an effect. You can't just prove that they're equal. That makes sense.
I don't think I really get it, but maybe we'll ask you again later. Thanks.
Okay.
We have time for one last very quick question while the next speaker is setting up.
So and maybe another one. I guess you must use monad transformers, not really monads, and have a stack that captures all the effects of OCaml. How do you deal with divergence?
I only implement things that terminate. And yeah, right now it's really like we have monad transformers for like state plus error together, things like that. But yeah, don't handle divergence. Basically, we want things that we can run in Coq, so we don't want to be able to write divergent computations.
Okay.
Okay, let's thank Josh again. And the last talk of the session will be by POPL'25 about a context cleaner.
Okay. Yeah, can people hear me? Yeah. So hello and welcome to my talk about general white box automation and the first step I've taken in that direction, which is a tape class guided context cleaner. So for the context, I'm a PhD student at Cambridge and I'm working on low-level semantics like assembly and weak memory style of stuff. And so I have a lot of goals that are relatively trivial, but still annoying to deal with by hand. So I've explored automation to solve those kind of problems. So what do I mean by general white box automation? I mean basically a hint-based proof search. So something that is general, can prove anything, provided the correct hint, and is white box. So it's as transparent as possible, and users using it are expected to understand exactly how the proof search works and debug it themselves. In particular, such a system would have the usual caveats that adding a hint can break later proof, and that adding rewrite hints can make rewriting not confluent. And that's not a problem as long as the user is able to debug those problems. So I'm not looking for any meta theory that would prevent those things from happening. So hint-based proof search places itself around here on the automation trade-off. So here I draw more on the left things that are more black box, more automatic, but have a high-level specification. The most extreme case being a SAT solver that is decidable and have a very simple high-level IP, a Boolean expression. But internally, it's quite complicated. But the user of the SAT solver needs only to understand what a SAT problem is. It doesn't need to understand how a SAT solver works, which is quite important. On the other hand, the more you go on the right, the more theory coverage you will have, but the more failure you will have. And so the user needs to increasingly understand how the tool works to debug it. And so the tools need to be increasingly white box and debuggable. I mean, the extreme being doing the proof by hand. And I think hint-based proof search has a very important point on that line that is not explored enough. So I try to do that. So what do we want from a hint proof search system? We want a good hint system, and here are some of the properties I'm interested in. So it needs to support backwards and forward reasoning as well as rewriting. I mean, ideally having something like int extern where you can inject an arbitrary tactic in your search is useful, but not necessary. And you also want to control well when ints are applied or not. So you want at minimum local export on global locality and some other things like, for example, you want to be able to enable a hint on a single tactic call. And ideally, you want to be able to group hints together, like group 5 hints together, enable them and disable them at the same time, including on a single tactic call. There is one last important thing with hints, which is that hints can be safe or unsafe. And the idea is that the user specifies whether a hint is safe or unsafe, and the system trusts the user on that. And that is critical for performance, because on a typical proof search, I expect to run something like hundreds of safe hints and very little unsafe hints, maybe even 0. And so on safe hints, I don't want to do any backtracking. If a safe hints apply, I apply it, and then I forget I applied it. Whereas unsafe hints, I do want to do backtracking. And the user is promising that somewhat applying a safe hints maintains probability. So the new set of generated goals are equivalent to the original one. So some example of safe action you can take is splitting a goal or doing a substitution, whereas taking the left of a disjunction or introducing a river are fundamentally unsafe. So I try to think about how to build a system that can do all of this using the existing Coq tactics. So I tried them, kind of failed. So first I look at Auto. So Auto is a quite nice white box proof search tool. It's easy to debug. You understand what it does. It applies in order, but it has some problems. In particular, Auto does not support any concept of safe hints. So you can kiss goodbye to any idea of applying hundreds of hints in a single proof search. Also, Auto naively only supports backward reasoning. Yes, you can hack it with hint extend, but if you just add a random X extend every time you want a forward rule, performance will blow up quite quickly. But it is good to keep in mind that Auto is a very good point in terms of debuggability and priority systems, because both of those things are very good for Auto. So I tried to explore other things. In particular, I tried SAuto from the CoqHammer project. SAuto is quite nice. It's very efficient on the theory it supports, but it's a bit hard to expand. Like, it's really black box. It's hard to debug when it fails. And it has what I would call a subpar hint system, in the sense that there are a lot of styles of hints you can't add at all. For example, if you want to do something like hint extern, it can only be safe. You can't add unsafe hint externs, and there is a bunch of other limitations. And it really feels in the API that SAuto was designed as a solver, which is fair enough because it was designed to reconstruct SMT proofs from CoqHammer, not that much to be used as a standalone tool. So I would say that Auto is a bit too much on the right of this line, and SAuto is a bit too much on the left. And so I'm trying to find some middle ground that has both good debuggability, a good hint system, but it's still powerful enough to do the proof I'm interested in. So I also looked at what other proof assistants do. In particular, I spent 4 months working on Isabelle, and I have some intensive experience with fast force and related tactics. So I'm saying fast forces, but there is actually 10 different names that more or less call the same proof engine with different priorities and heuristics. Fast force is maybe the most well-known, but not the only one. Then Lin also developed ISOP, which is a decent white box search, but I've never used it, so I can't talk much about how it's actually usable. And then Auto and SAuto I already talked about. And so if we start comparing them, so first we note that both fast force and ISOP supports all the style of hints I want without any limitation, which is naively not the case of Auto and not really the case of SAuto. Like, there are some asterisks here. Furthermore, an interesting data point is that fast force does not support arbitrary tactic, as far as I know. ISOP does, Auto does, and SAuto has this safe limitation. And despite that, fast force is still considered a good tool. So that's an interesting point. Then the safe and unsafe distinction is supported by both fast force and ISOP, and I think that's the critical bit that makes this tool actually good in practice, and what's missing in Auto. In terms of priority system, fast force doesn't have any explicit concept of priority. They have kind of accumulated 25 years of heuristic that guess in which order to apply hints, which make it decent in practice, but it's not what I would call white box. And in terms of debuggability, fast force is already quite annoying. Like, if you call fast force and it fails, it's quite hard to understand. Whereas if you call Auto and it fails, it's really easy to trace it and understand exactly the sequence of steps it tries. So there is some things to be done there. ISOP, I have no idea, I've never tried. So that's kind of the landscape I felt I was in. And a last very important point is that both Isabelle and Lin have a good built-in simplifier that those proof search tools are actually actively using, where Coq doesn't really have what I would call a good built-in simplifier. Like, yes, you can hack rewrite strat to do some stuff, but it's not really great. So that leads me to what I think we need to do to get a good general white box proof search architecture in ROC. This is not new. I'm just basically stealing the architecture of the other proof tools. So first, we need a good simplifier, so something that can do efficiently rewriting and computation, so more or less what you would expect from rewrite strats and CBN, all at the same time and efficiently. Once we have that, we need a clarifier, so something that can run all the safe proof steps in sequence. That includes calling the simplifier, but also things like doing safe reasoning, like what intuition does, do safe equality reasoning, like what simplify ec would do, and some other safe stuff, something that would look like Isabelle clarify. And once we have that, we can do a proof search by just running the clarifier, trying one unsafe step, running the clarifier, trying one other unsafe steps. And here we need to think about depth first search or best first search and priority system to know in which order to try unsafe steps. In this talk and in my own work, I've focused only on the clarifier, so I won't talk much about the other two. So cdestruct is my clarifier for rock. So it's designed by having a core tactic in LTAC2 that's not very long, like 50 lines of LTAC2-ish. And that applies some steps in order without doing any backtracking. And it pulls from a tape class in system which steps it should apply. So some example of what it can do is case splitting. So taking inductives in the context and breaking them down. Similarly for the goal, taking an n in the goal, splitting it up. Then it can do injection and discriminate. It can do computation, so it will happily call CBLN regularly. It can replace propositions, so take a proposition, replace it by another. This looks like rewriting, but it's not really rewriting. Like cdestruct has no built-in system to like rewrite under anything. It will just take a whole level proposition and replace it by another according to a tape class. So I've done some very hacky tape class, hackish programming to remake that into somewhat a rewriting system, but it's not great, and we really in desperate need of a decent simplifier. Then it can do substitution, and it can do match case splitting, which are also quite usual things to do. So how would you use it? So if you don't give any hints to cdestruct, it's basically useless. So there is a default database of hints that handle like standard logical connective, and then the user can add new ones. So for example, to tell cdestruct to break an end in the hypothesis as soon as it sees it, you just add this instance, and then cdestruct will pick it up. Then you can add a rewriting instance. So you tell cdestruct to replace is sum of O by there exists an O. So there exists an X such that O is some X. And then this instance will contain the actual equality proof. So when you do the dots, then Coq will ask you to prove the payload of that tape class. The cdes case has an empty payload. And if you want to gate a tactic by an option to, for example, have multiple instances that you enable together, you can create an empty class and use that as a gate. And so, for example, the splitting of AND in cdestruct is gated by the cdes split goal option. And so this instance will only be resolved if the cdes split goal option is enabled. And so cdestruct will only perform that operation if you enable that option. And you can enable that option either by making up a dummy instance of cdes split goal globally, or by setting it when you call cdestruct. So you can call cdestruct with a set of hypotheses and some intro patterns for goal hypothesis to work on. And then you can do hashtag an option and hashtag other options to enable specific hints that you want for this specific tape class call. So now I'll show, and so all of this about tape classes is quite important because I found that it's a relatively decent hint system in practice, especially with discrimination tree. You can reach a relatively fast lookup in terms of which hints to apply. So it's not perfect, but it's also not terrible. So what it can do in practice, I will give some example about a dependent map implementation I've done. So a dependent map is a map where the type of values is dependent on the type of keys. So I just implemented using stdpp gmap. So if f depends on k, then I just have a carrier, which is a gmap of k to the dependent pair of k and f of x. And then I have a soundness predicate that says that the first component of the dependent pair is the key. And then I want to prove lemmas, like if I insert value v at a position k in the map and then look up k, I get v again. And so how to prove this? I just unfold the two definition. I get these big ugly things where I do a match and an inspect, and then I do some transport. And then the corresponding operation, insert and look up on the underlying map carrier. And then I can just call cdestruct on this, and it will entirely solve it without doing any unsafe steps, because there is no unsafe steps to be done here. So what cdestruct will do, it will break up the match. And here I will first handle the sum case. So in the sum case, the match discriminate is insert with lookup is equal to some s, s being a dependent pair. Then it breaks up the dependent pair. There is nothing to do on x of type k, so it inserts it. Same for f. Then for e, I've taught cdestruct with enough hints about map theory, so it's able to simplify that. But it counts directly in place because E is actually used in the obligation that's in the transport equality. So what cdestruct will do is make a copy and simplify the copy and block the original. So, and in the copy, it knows enough about map theory to know that doing the lookup after the insert gives the same thing, and so it gives the equality of XST. So then the block things needs to be introduced because you can't work on it any further. And then you have XDST equality. So the cdestruct is able to extract the equality of the first component and the substitution. So we substitute K to X and revert anything that's modified by that substitution. Then we keep processing. There is nothing to do here, nothing to do here. Then we again have an XDST equality, but this time the first component unify. So this simplifies into an equality of the second components. I do use UIP. And then there is a substitution again to be done. So V into F. So we revert everything again. Then we reintroduce the block thing. Then we can do a computation. There is on the right .t2 of XDST, so we can do the projection. Then we can peel out the sums. And then this transport, the source type is f of k, and the target the type is f of k. So the transport does simplify. And so we end up with v equal v, and then reflexivity. And the non-case is much less interesting because given map theory, cdestruct knows that this simplifies to false, and so can also solve the non-case trivially. So I found this tool to be useful in practice, not just on dependent maps, but on many other goals that I've encountered. And it kind of gives me a feel similar to Clarify from Isabel, despite the lack of simplifier. So I kind of hacked together a bunch of logical programming and type class rewriting system to pretend I have a simplifier, but I don't. So that's something I want to keep working on. The lesson I learned is that for this kind of project, extensibility of your tactic is critical. So being able to add new rules without going back to the tactic definition is really important. And debuggability is also critical, otherwise I would have gone mad a long time ago. So you can run cdestruct step by step. So there is just a cdestruct step tactic, it will do one step. And you can just copy paste it 100 times and then run it by one and see when it does what you don't want it to do. And I've also learned a few things about opacity. So for this kind of stuff to work, you really need all constants to be opaque in type classes by default. That basically results in a 5-time speed up in both cdestruct and setoid rewrite, by the way. There are still some performance issues with discrimination tree, sadly. So in particular, if you start doing research on transparent terms, discrimination tree have a tendency of giving up the discrimination tree and just trying unifying with everything, which destroys performance. And lastly, I've discovered that injection completely ignores any concept of opacity, so I kind of re-implemented injection as part of cdestruct to have a version of injection that does respect opacity. So these are some of the things I've had to do. Sadly, this is not my main topic, so I will have limited bandwidth to keep improving on it. But the thing that remains to be done is mostly actually do a good simplifier. So either by improving rewrite strats or keeping doing type class rewriting like I'm doing, but in a more principled way, or then there is the approach of reification and writing a verified rewriter. I don't really know which one is the best here. And for the proof search, I mean, one can think about improving auto and adding, for example, an option for safe hints, or we can write a custom tactic. And if we do that, then there is a question of LTAC2, LP, or OCaml plugin, which isn't fully clear to me. After watching the talk on LP, I'm not entirely sure that my choice of type class logical programming and LTAC2 was the best. But hey, it's done now. So far, this is not a standalone repository. It's part of my main project, but I'm happy to split it off if people want to try it and work with it. So are people interested? Let me know. Here's the code and the documentation.
Questions?
Thank you. Definitely interested in at least some of this. In particular, I was wondering if you could say a bit more about what you have in terms of forward reasoning, because to me, that's like the biggest thing that's missing from the standard ROC toolbox. I mean, you can wrangle auto to do a lot, but forward reasoning, I don't know a nice way to do that.
So yes, so I mean, you can tell cdestruct to break any inductive you want or not break any inductive you want. Then I mostly do so far my forward reasoning by rewriting proposition into a regular logical projective that then will be breaked up by cdestruct. Since I'm not doing any unsafe stuff yet, I won't take a risk of applying something that would like reduce the probability of the goal. That's something of a next step I'm thinking about, but I haven't done that yet. But I do a bunch of things that you would expect like simplify AQ to do. Basically all of it, and a bit more because I also do a bunch of dependent simplification, like what you would expect. The kind of cleanup that dependent destruction does.
Okay, but there's no like, I don't know, apply the set of lemmas forwards until saturation and then go on and keep using those facts or something like that.
Saturation is something I've thought about, but I haven't really done yet because I'm a bit worried of blowing up, as all saturation thing is. I have some idea of doing it, but I need a bit more work, and I'm also afraid about how much it would kill performance. But basically, yes, cdestruct has really this idea of, I'm done with this hypothesis, I can move it to the context and not work on it anymore, so it really does it in order. And so this would be a good place to insert like saturation hypothesis, because then once the hypothesis is processed, you won't start looking again for saturation hypothesis. But I haven't actually tried that yet.
Something that I encounter a lot is like a particular goal is easy to solve using a particular assumption I have, but I don't want to add that lemma as a general hint, because then it will always try applying this, and that could easily go wrong in the completely wrong direction or something. I'm not sure if you have a nice way to represent it.
So right now, I don't think I have. I mean, one thing I do sometimes is rewrite a goal depending on hypothesis I picked up. So like if this hypothesis is in the context, then I can simplify that goal into this other simpler goal. That I can easily do. But I don't, I mean, since this is a clarifier and not an actual proof search, I don't have generic way of just applying a lemma based on some condition. But I do intend to, if I do a proof search, which is somewhat my intention, then I do intend to support these kind of things.
Okay, cool, thanks.
I think time for one last question.
I think you should actually take a look at Janis Lindberg's thesis and Aesop, because it has basically exactly the same motivation and like design as what you've been talking about.
I've read the paper, but not the thesis.
But what I also wanted to mention that one of the downsides that we found with Aesop is that you really need to have integration with the library. Like, you know, it's not good enough to just have a white box automation, because if you need to add hints for it to be useful, then if the library doesn't have the hints, then people aren't going to be bothered to add the hints on the spot when they're using it in application. So it's really important that like you coordinate with the libraries that you're like the upstream libraries that that users are going to be using with your tool.
No, I mean, to be fair, I mean, in my own project, I'm perfectly happy to adding the hints myself because I know it's worth it. Teaching people that it's worth it to write hints is a problem I haven't considered that much yet.
And a lot of users will not necessarily know what are the, you know, they won't actually know enough about how to write hints correctly and how to construct conflict rewrite systems. Blah, blah, blah.
It is, I mean, unless you are provided the hint database that already works out, it is a power user tool. I'm afraid of that. But it's not because it's only useful to people that are power user that it's not useful to make.
Okay, let's thank Thibaut again. And there will be coffee and tea on the 3rd floor, I think.
the new logo for Rock, and we have some kind of guideline on how to promote Rock also on your own websites and papers and so on. So for example, this is the kind of logo we expect you to build when you want to do a workshop based on Rock. Like you put the name of the workshop just below Rock, like this, or this kind of stuff. And as you will see, there is a new website that has been announced to the happy few on Discourse during Christmas, and that will be launched for real today. So a bit of so traditionally we present the timeline of the current evolution of version of Coq and now Rock. So I think it's from today. We have the Rock 9.0 release candidate version. So this will be the first version mentioning the Rock name. And as you can see, there is a Rock platform. So I will come to this just after in a minute. But the platform is the kind of consolidated distribution of Rock that is available both mainly for Windows and Mac users. And it contains both Rock and a lot of libraries of the ecosystem that are consolidated into a single binary, so that, for example, for teaching is very convenient because you can tell your student to just install the Rock platform and hopefully it works out of the box. And they have a lot of libraries like MathComp and everything coming with that, so they don't have to bother about installing things. And so there is a slightly delay between the Rock platform release and the official release on OPAM, because we need to make sure that everything fits, and we need to have the signature of the binaries for Mac, which is kind of a big issue. But in the end, we managed to make it work. And so the Rock 9 release, the official one, is expected to come in March, but you can already try it because now there is the release candidate. So a bit of outline of what I've been talking about. So as I say, I will present the Rock platform quickly for those who don't really know its existence yet, even if I think it's quite well known now. And there is another Rock platform thing, but it's for the documentation, and this one is a bit of much more new. So I think it makes sense to advertise it a bit and to ask for some help from the community to make it bigger. I will also present a bit about a Docker support that we have for running your Rock project. Sorry, I'm not used to it even myself. I will also make a focus on the standard library because we made a kind of a big move by putting the standard library outside the main repo of Rock, so that the standard library, a bit as the MATLib library for Lean, can live its own life without being completely entangled with the development of Rock. And then I will present the newest feature that have been integrated into Coq 8.20 and some of them into Rock 9. I will also do a quick focus on metaprogramming facilities. This is a bit more for the record because Enrico presented most of them already, but because the slides sometimes stay on the web, I think it's good to mention them in the slide, but I will go quickly as Enrico did a nice talk on this already. And then I will show you the new Rock website and what's inside, so to just give you some hints at what you can find in it, and maybe ask for some help in making it even better, because we also need help from the community to fill it in with the universities that are teaching Rock and links to the lectures and so on. This we don't know, and it's good, and it's very easy to do pull requests on the website because it's just markdown files that you need to edit and to put your own data in it. Okay, so let's start with a disclaimer. So we expect somehow that most projects will rename their own project names with Rock, but we don't really force people to do it. I mean, we let it to the user. So for example, for CoqPL, I guess will be RockPL in the future, because CoqPL is not a very nice play word. It's just Coq and PL. So for this kind of project, we expect the renaming to occur. But for other projects like Cocktail, maybe this one is funny, so it's a bit weird to rename it Rocktail, or why not? I mean, we let it to the user, but in the Rock ecosystem, the closest to Rock, we try to rename everything, but then for others, we don't really have any policy. So in the presentation, I rename everything rock, but sometimes on GitHub it's still Coq because the change has not been fully done. So let's focus on the rock platform a bit. So the idea is to get a coherent distribution of the rock prover together with a lot of packages. And so even if there are scripts for Linux distribution, the main goal is to have something easy to do in Windows and macOS for non-expert user. And it's customizable, so you can also pre-select some kind of package list if you don't want to get the whole ecosystem. And this is very easy to configure. And what I want to advertise on this is that we have currently an open engineering position for taking care of all of this, because currently we have Michael Socktrop that built the initial state of the thing, but he has no time to, he's not at all full time on it. He's already very nice to did that. And we have Romain, who is an engineer in the rock consortium, but his main goal is to develop the VS Code extension for rock. So he's helping on the rock platform, but we have an engineering position so that we can have a solid rock platform in the future. So if you know anyone who could be interested, please put they in touch with us. Now a bit on the rock platform docs. So I don't know if you heard about it. It's a new initiative, mainly led by Thomas Lamiot, Pierre Rousselin, and Theo Zimmermann, in order to get a very nice and comprehensive documentation platform for users of rock and of rock libraries. So we aim to have tutorials and stuff like that, and how-to on the platform. And again, it's based on GitHub and pull request, so it should be easy to provide your own tutor, and you can also do issues or enhancement proposal to request a tutor. But it's better if you contribute and do a pull request and put your own tutor in it. So here's the link. It's GitHub Coq platform docs, and hopefully in March it will be a GitHub rock platform doc. And so that's maybe all I have to say here. With respect to Docker support, so maybe not all of you are aware of that, but we provide official Docker images for all versions of Coq and now Rock. And the idea is to make easy for you to develop a CI to test your own project and so on. So you can rely on Docker images to do that. So there is a Docker hub thing. If you have more questions about it, I'm not the most technical guy in the team, so if you have a technical question about it, I hope Enrico or Mathieu will be able to answer them during the Q&A session. But just to make you aware that this exists, and it's very helpful if you want to rely on the CI on your project. CI testing each pull request. Okay, so now a big focus on the standard library. So we made a big move into splitting the standard library for the main rock repo. And as I said, the main idea was to ease contribution to the library, because I guess it was a bit intimidating. If you want to contribute to the standard, if you wanted to contribute before to the standard library, you have to do a pull request on the whole Coq repo on GitHub, and it's very visible, and we have policies to do that and so on. So it was a bit overkill for just adding a new lemma in the standard library. So I guess it will be more user-friendly now and less intimidating to do it. And the idea is also to have a separated team for dealing with the standard library, even a team that is not constituted from Rock developer, but from Rock user and from the community. And as I said, we welcome new contributors to this library. And and the idea is that maybe not to focus on only this one, but to make it easier to interact with std and other stuff, matcomp and so on, so that we can have a better sharing across them. And it's also connected to what I will present about the new core library that will be fully sort and universe polymorphic in the next version of ROC. And that can be used by the std, but also by other libraries for ROC. What do I forget? Yeah, and one of the nice things is that now that it has been outside the ROC main repo, we can compile the standard library with a full version of ROC. So we can use LP, we can use equations, we can use everything in the standard library. Whereas before it was a bit intricated and the compilation chain was a bit of a nightmare. So we refrained ourselves from depending on equations and LP and so on. But now the ROC core package comes with a core lib version and equations and LP, and you can import them, and then you can make your library depends on all of this. So it's a better bootstrap, I guess. And again, we will launch a call for maintainers and contributors, and the idea is to make it able to, like the std define its own roadmap and pull request strategy and so on, really independent from ROC. Of course, it will be like we will be watching it and maybe try to advise and try to be in the kind of steering committee of it again. But yeah, maybe you need to wait for the mic.
Should we use the same RFC repo for std proposal, or do you want to handle that separately?
You mean the
CEP repository?
For the enhancement proposal?
Yeah, so should we use the same system for the standard lib, or do you have another pipeline in mind?
No, maybe the same, but a separate. I mean, in a separate repo. But yeah, we leave it to the maintainers to decide somehow. The Coq enhancement and work enhancement proposal seems to work, but maybe we can do. I mean, we left it open to the community somehow to decide how to contribute and make it evolve, if it's the question.
Yeah.
Okay. So now a quick focus on the main new features. So I just want to mention LTAC2 improvements, even if I will not be talking about it. But so we have seen during the week that already some people are using LTAC2. There were some limitations that have been fixed. So now it should be kind of production ready, so you can really use it. You can also use a ROC LP, of course, as well. But I think they combine together well. But I will more focus on two new mechanisms that we have been integrated. So sort polymorphism has been integrated in CoQ 8.19, I think, but it was not supported at all with the rest of the system, like tactics and so on, so it was not really usable. Now it's better, so I will show you the new core library and how it works. So I don't know if you have been there at the very last talk of the very last session of POPL, but my student presented the sort polymorphism thing, so but I will do another focus on it. And we had a new system to be able to add axioms that compute. That it has been also integrated in Agda, but a bit later in ROC. And so it allows you to experiment with. So instead of just adding axioms, sometimes you add axioms and you say, oh yeah, but I know that my axiom could compute in some way, but there is no way to tell the conversion of ROC to do it. And now there is a notion of free write rule that allows you to define your axioms and the way they compute. So I will show a very dummy example and a more evolved one during the demo. So I guess it's time for the demo. Let's hope it works. I don't see my mouse. Yeah. So I will just show you what sort polymorphism means. So maybe it's too small, so make it bigger, one time bigger. Yeah. Close this. Okay. So the idea is that most of the basic definition in the core library were duplicated between type, prop, and now that we have sprop, it was triplicated. And here it's the case of sigma type. You want me to make it one time bigger, or it's okay like that? No, it's okay. Maybe. Yeah, it's okay. Okay. So this is the dependent sigma type, and as you may know, in the standard library there were sigma, sig, sig-t, exist and whatever and so on. And even some versions for SPROP were not even defined because nobody took the took the initiative to do it. So in the end, we end up having a lot of duplication in the inductive definition, but also a lot of duplication, a lot of duplication in the lemmas that were proven and the functions. And I guess I'm not the only one to ask myself, oh, what is the name of the projection? Is this proj1, proj-t1, proj whatever? So it was a bit of a nightmare. And the idea of sort polymorphism is to use prenext quantification as for universe level. So here it's for the universe level, but at the level of somehow the quality of the universe. So here it's a variable, but then the meaning of this variable is to be substituted by either prop type or sprop. And in the future, maybe with new sorts that you can add in the system. And you could even use it to develop your own extension of the type theory of rock by declaring new sorts and new axioms that only works with your sorts. And this way you have no problem of consistency because you can kind of localize them in some sort, and the interaction with the main prop and type universe can be kind of localized there. And with rewrite rules, you can extend the type theory this way. And so here we have now in the core library, hopefully for rock 9.1 or something, it will be merged, and we have only one sigma types with only one projection, two, but one notion of projection. And then what we do is to stay compatible with the current version of the state of affairs of libraries, we provide wrapper to say X intro is just the canonical X constructor, but we fix that some of the sort are prop and so on. So we still have the combination, but the combination is not a new definition of a new inductive type. It's just a notation for some particular instances. And then we can prove general lemmas about that, and get as a definition or notation the previous lemma that were before. So for example, if I go to the unit type, now we have only one unit type, which is sort polymorphic, and then we have notation for true, which is the unit type in prop, just being instantiation of unit at prop, and the silly name, the I don't know why it was I, but why not, is now just a notation for TT in unit at prop. And to stay compatible with the previous stuff in the rock ecosystem, we just provide the register things with in unit, in true, and so on. But in the end, we register always the same thing because now a single unit type works for every universe. And so what will be also we make use of this also to simplify a bit and to unify how rewrite and setoid rewrite works. So I don't know if you have been using this, but the setoid rewrite is a notion of rewriting that is based on relations. And there were relation in prop, relation in type, depending on what you wanted to do. A lot of duplication in the code. It was very hard to maintain. And even when we have been ported, so now there is only one single sort polymorphic version. And when we did this merge, we realized that actually the prop and type libraries were quite kind of not complete. I mean, some lemmas were in prop and not in type, but some other the other way. So that's why sometimes you rewrite, it works, and then you do the same rewrite in type, it doesn't work, but just because the lemma is missing. So it was really weird. And so now we base the setoid rewrite library on one canonical notion of relation that takes, so relation is from A or A because it's a relation, but the A can be in any universe S, and the relation also can live in another universe S prime. So you can define a relation over prop in prop, or over prop in type, over type in prop, and so on. So there is only one single notion of relation, and the whole classes, morphism, proper machinery works on this generic notion of relation. And similarly, as a way to do some unification here, we have moved to a generic, an abstract notion of equality. Oh, where am I? Sorry. So we define an abstract notion of equality, and we base all the rewriting on these instances of equality. So we say an equality is just a type for all A in some universe, a row, so it's just a relation somehow, a polymorphic relation. And we don't fix the universe for the type on which we are looking at the equality, nor for the type of the relation. And what we just ask is that there is a reflexivity method for it, and there is a J eliminator in the Martin-Neuf style J elimination. And then all the machinery of rewriting, discrimination, so the discriminate tactic and so on. Actually, they were doing explicit pattern matching on equality, but it was not required at all. They can just be parameterized by some arbitrary elimination. And so we have reworked all this so that discriminate, rewrite, and so on, they work with any sorts and with any notion of equality. So that's pretty nice, I think. And then using this, so this is a bit ugly, but it's in the core library, so you don't have to write it. But now we can prove generic lemmas on equality by being parameterized by arbitrary equality that satisfies the relation. And then, of course, as we want the system to work as before, we can still define the standard equality as an inductive type and show that actually we have instances of all the reflexivity and elimination rule of equality, but now the equality, the inductive equality that uses an index is just one particular case of a nice equality with which to rewrite, but it's not the only one. And this maybe led me to rewrite rules. So what are rewrite rules? They are just a way to postulate axioms, but we have a special keyword, which is not axiom, but symbol. And the idea is that this axiom can be used as something on which you can match and define rewrite rules on it. So this is the favorite example of Jesper Cox. This is the parallel plus. I don't know why he's fond of this example, but you always want to do it. And so parallel plus is something that you cannot implement in the rock theory because you need to decide whether you match first on the left or on the right. And there is no way to do some kind of parallel match because it can be very dangerous in the general case. But here it's simple enough so that we are sure that it's not too crazy. And so because it cannot be defined internally, you can postulate it. And then you can add rewrite rules that emulates this parallel matching. Oh, sorry. Okay. And then if you compute here, you will see that this is not useful. I will do it. So if you compute this, so you can even mix the normal plus and the parallel plus, and you can put everything at the same time. And here, if you compute, you just get what you expect. Like all the constructor are at the top, and the parallel plus is just blocked on neutral terms on the variables that because there is no meaning yet for them. So this is a simple version of rewriting, and I just wanted to advertise a particular use case of rewrite rules in order to define observational equality. So as I said, we have now a canonical framework for doing rewrites and so on with an arbitrary notion of equality as soon as it is reflexive and it satisfies J. And here what we can do is that we can say that the equality in S prop, so this is the one that you should not be able to eliminate as an inductive type because then the type checking is undecidable, even if Lin decided to do it anyway, but they have another approach on undecidability than we have. And so here we are using the notion of observational equality that comes from the work of Connor McBride and Thorsten Alterknich in the beginning that we have improved now. And so we just, so the observational equality, because equality is natively proof irrelevant, because in S prop every proof term are equal, it satisfies UIP on the nose for sure. But then the thing is, how does it compute when you transport an equality when you do the elimination? And actually, the observational equality doesn't look at the proof because somehow the proof is a black box. It's a proof irrelevant thing. It looks at the types, like the normal cast, because we are programmers in the room and we know how to cast between two types. And somehow the proof of equality is useless. It's just a witness that the cast will never fail, because you have the proof that it will go to the end. And so we can postulate this symbol, and with a cast you can define an eliminator, and so you can provide an instance of elimination, and automatically you can do rewrite on this new equality, even if it's not based on the inductive one and on matching. It's just based on another elimination principle, and you will have all your traditional machinery working with ROC. And just to show you the use of rewrite rules, so it's a bit ugly with universe level. We hope to fix this because we have still a bit of minimization to improve. But the idea is that you need to tell the system how cast computes on a weekend normal form somehow. And so here we say how to cast between a for-all type and another for-all type. And it's just the obvious thing that you do a lambda. So the cast of a function is just another function that somehow casts its argument in one way, apply the function, and cast the argument in the other way back. It's a bit hard to read because of the notation for the moment, but it's just this. And because the equality is in S-prop, and we can add axiom, so we call it parameter because it looks less frightening than axiom, but in the end it's the same. You can add the prop-x axiom, that fun-x axiom, and they are perfectly fine. And they will not block computation because we never compute on the equality. So in this way, you can have a setting with UIP, fun-x, prop-x, and you can rewrite with everything, and you still have canonicity. Okay, so that was just an advertisement, but it's for the future. Welcome back to the present. So this is, I don't want to go into detail because this is the talk of Enrico, but we just wanted to emphasize that there are two new metaprogramming facilities for ROC. So ROC-LP that you have seen with those projects that we recommend to have a look at. In particular, hierarchy builder for those who are building complex mathematical hierarchies is really a game changer. And there is also MetaRoc, but I guess this week's many talks have been using in some way CertiCoq, Verify FFI, WASM stuff on WebAssembly. But this is another way to do some metaprogramming in ROC, very different from ROC-LP. So to my understanding, they are very complementary because what you can do in one, most of the time you cannot do in the other. The table is almost red, green, and the other way, but it's almost never red in the same on the same line. But if we manage to make them interact well, it's not an issue. Okay, and last thing I wanted to talk about the new website. So I don't know if you have seen it. Some of the talk were already using the new logo, so I guess some people at POPL were already aware of the new website. Just a bit of history of the website. So it's written in OCaml fully, or EML, but yeah, mainly OCaml. And it's just a fork of the OCaml.org website, which we found very nice. And it was already, I mean, it has been made by the Taridas team with the idea that it will be reusable and so on. And that's true. It has been very easy to port it to ROC. We have a new visual identity thanks to Bastien Sozo, who developed all the logo, the colors, and the typo. And so now the website is with an automatic deployment and a staging branch to test on a branch that is not already visible by users. So it's very easy to upgrade, and you can upgrade it through pull request or just opening an issue if you don't want to implement the pull request yourself. But then there is a CI that ensures you that you have not break the website and so on. And as I said already in the introduction, contributions on the framework it's ML, but on the content it's just Markdown. that is parts to produce the HTML. So if you want to contribute by just, for example, saying that in your university there is a lectures on rock and you want to put it on the website, it's just a pull request editing the Markdown file. So it's very, very easy. And as you will see, there is a nice integration of the rock platform, rock.platform, and OPAM packages. And so again, please contribute to kind of fill in the website with the thing that you know and that we don't know. So you can put podcast on rock or whatever, success stories for your for your project. As I said, lectures. You can put papers, PDFs. And so this is the new website. I click on it to show a bit how it works. So we have, this is the main page. We have a bit of history here. So for people who want to know about the previous name and so on, we explain a bit how it works. I will let you read when you will have time. So the platform is integrated in the, maybe I will zoom a bit. The platform is integrated into the website. And from the website, you can see all the packages that are integrated in the platform. So it's, the list is a bit long, but then you can do search in it. We have also integration of OPAM, or maybe a bit zoom out now. So thanks to, so the OCaml.org website, of course, already have an integration of OPAM packages, but we just reuse it. And here you have the, so there are currently 467 packages on at the top of Rock, including Rock. So they are not all renamed, as you can see, but and you have the most used, the new packages, and you can do search here. So if you want to see which package mentioned LP, so you have up. So it's quite nice. It's easy to navigate inside this, and we provide also stuff for the community. There is a new way to announce stuff with a Mastodon account that has been created recently. And then, as I said, you have stuff about universities. So wanted to focus. So you have. So Mathieu did hard work this morning to integrate the new release on the website already. So you can see it here. This was the announcement for Christmas that is still appearing here. And where are the universities? Yeah. And for education, you can click and then you get which universities are teaching rock. And as I said, you can have a full list here. And this is where we expect users to be able to keep this list up to date. So if some links are deprecated, or if some lectures have been cancelled and so on, remove them and add them, so that the list of universities that teach rock is up to date. So that's the idea of. We did the first version, but then we expect the update of the website to be collaborative among the community. And it's just currently it's just. Oh, it's not finding it. Yeah. So it's just on GitHub, and it's a normal GitHub project with a pull request and CI and everything. So it's very easy to modify it. Where? I guess I'm almost done. This is not what I wanted to show. I'm a bit lost. Yeah. So the next release expected in March, next March. So for those who have been struggling with template polymorphism, if you know what it is, now template poly is fully based on sort polymorphism. So there is no ODTs anymore. It's just part of sort polymorphism. And also the inclusion of prop into type will be removed probably in the next version. Because it's also now subsumed by sort polymorphism. Somehow the subtyping stuff was a bit of a hack to get some kind of flavor of sort polymorphism where it was not implemented. So the splitting of stdlib will be effective for this version of Rock. And And we have a new command line interface. So you can still use CoqTop and CoqC if you have your Makefile doing this way, but the new way of doing it is just using Rock, and then Rock REPL, Rock Compile, Rock whatever. So I will let you, you can see in the changelog how it works, but it's basically just to make it a bit more modern. And currently we still have the Coq in AI4 website. We don't have the redirection yet because it will have broken a lot of stuff. But when we'll do the official release, then we'll move and change also the organization to Rock. And just a bit of advertisement for the future. So I don't know if you have difficulties with universes if you're using polymorphic definitions, but Mathieu Sozo worked very hard to get what we call algebraic universes. So this is universes where a version in which you can do +1 and max everywhere in the type. There is no restriction anymore, and the system is aware of that, and a more reliable minimization process. So we expect this to make it possible to use universe polymorphism massively now. As you said, it's still on progress because in some of the Rock file that I've shown, there are still some universe level crappy, but it's very in progress. The full polymorphic library, as I shown you. So the new notion of equality that is very generic, and so you can even think that you could postulate your cubical equality with univalence, and you will have Setoid rewrite working on it and everything. We have some unification performance that are in progress. And also in the pipeline, there is a very native integration of equation to pass it into the main repo of Rock so that equation is available from the beginning and without any weird stuff, and smaller version as well. Okay, so to sum up, please contribute to the website. Please contribute to the Rock platform docs. Please contribute to the stdlib. And there is a reminder that there is an open position for dealing with the Rock platform if you have any engineer in mind that could do it. And that's it for the Q&A session now. So I guess we'll have to switch the laptop thing, but you can already ask questions.
Hi, this is Mohit, and I have I'm curious to know if there are any existing plans, or are you planning to integrate, let's say, LLMs with a Coq pipeline so that it's easier for a newcomer to navigate Coq and learn Coq and experiment with Coq using LLMs?
LLMs. Yeah, we have some projects starting on this. You mean about like writing in native language and having LLMs understanding a bit?
Yeah, or using LLMs to actually navigate different Coq libraries and like produce some examples that they can use as a boilerplate, and then as a boilerplate to finish up the proofs or compile in Coq.
Yeah, there are projects starting a bit on this, but we have no very nice product-ready things to show. But yeah, we are thinking about trying to make this improvement.
Okay, that's cool. Thank you.
But it's not for the near future. So yeah. So Mathieu Sozo, Gaëtan Gilbert, Pierre Roux, and Yves Berthaud seems to be online. Mathieu is there. So it's 8 p.m. in Nantes, I guess, something like that. Not too late. You're all muted. I don't know if you want to. Yeah.
Hello.
Yeah. I guess you said hello, but the sound is not set it up yet.
Better?
Yeah.
Oh, cool. Perfect. Where's the cursor?
Oh, cursor is down there. Trying to move it to its trap. Oh, okay, got it.
Okay, perfect. All right. Hello, my name is Calvin, and Gary and I are going to talk about our experience on the Vellum project for formalizing LLVM. Before we start, we'd like to acknowledge all of the collaborators, institutions, and grants which have made Vellum possible. There's a lot of them. So this talk is going to be a bit of a whirlwind introduction to Vellum, a formalization of the LLVM-IR in the ROC proof assistant. For this talk, we'll give a brief overview of LLVM, its complexities, why it's worth formalizing, and we'll discuss the state of the Vellum project and its overall structure a little bit. We're going to briefly talk about our experience on such a large formalization project in ROC, what's working well, some pain points we've encountered, and what we'd love to talk to some people about. And finally, Gary will conclude the talk by talking about some of our differential testing work. So LLVM is a common compilation framework. It's used by a variety of front ends in order to generate efficient native code. And at the heart of LLVM is the LLVM-IR, which is an assembly-like language which can be used as a shared compilation target for many compilers. This intermediate language also enables shared optimization and analysis passes. So LLVM itself is a bit like a high-level assembly language. Translating C programs to LLVM-IR is fairly straightforward, as these languages operate at a similar level of abstraction. LLVM is just a bit more verbose. It has more assembly-like instructions and more explicit branching. But notably, LLVM-IR abstracts away many of the details that you would find in a typical assembly language, such as the usage of machine registers and calling conventions, sort of. So LLVM-IR is actually quite a big language, which makes it difficult to understand. For instance, here's the table of contents for the informal language reference. It's kind of intimidating. And even though LLVM is a large language, a lot of the complexity arises from how small features interact with one another, especially when we consider optimizations. To demonstrate this, let's just zoom in on one little feature of LLVM called onDef. OnDef values are used to represent indeterminate bit patterns that you get in situations like when a variable is uninitialized. OnDef is useful because it gives the compiler additional flexibility. We don't have to keep track of a specific arbitrary value for an uninitialized variable. Its value is allowed to fluctuate over time, which can enable optimizations and ease register pressure. This is a somewhat artificial example, but because x here is not given a specific value, the compiler can assume that it can take on whatever value is most convenient for it and leads to the best performance. In this case, the compiler might choose a value which avoids the expensive branch. OnDef values can interact with optimizations in complex ways, however. Sometimes they allow for more optimizations, as in the previous example, but OnDef can also complicate certain kinds of POPL optimizations. So for instance, we can't transform a multiplication by 2 into an addition if the value being multiplied is OnDef. Multiplying an OnDef value by 2 gives you a non-deterministic even number as a result, but adding a value to itself, adding an OnDef value to itself yields a non-deterministic set of all possible numbers, because the OnDef value can actually take on a different value at each usage. And so these results aren't equivalent, and these instructions therefore can't be used interchangeably. So some features of LLVM have complex interactions, particularly in the context of optimizations. It can be tricky to know what optimizations are valid with all of these subtleties, and this can lead to end-to-end miscompilations. Indeed, features like OnDef are complex enough that many miscompilation bugs have popped up because of it. For instance, the Alive project has run into so many optimization failures due to OnDef that they had to automatically filter some of them out. So let's talk about how we hope to wrangle LLVM. LLVM is an important language used by many compilers, but it's a complex language, and subtle interactions between features can lead to miscompilations. Building a formal specification of LLVM in ROC should help us understand all of these subtleties and provide us with a platform with which we can verify the correctness of various optimization passes. This is the goal of Vellum. The structure of Vellum is roughly as follows. We're going to take the informal specification of LLVM and convert it into a formal description of the language in Rock. Naturally, we have an abstract syntax tree for LLVM-IR in Rock, and we will model control flow by denoting this abstract syntax tree into an interaction tree. Interaction trees are a kind of co-inductive free monad, and we use them to represent program traces. The co-inductive nature of I-trees allows us to represent possibly non-terminating programs, and using the free monadic structure of I-trees, we can divide the language into events, which can be handled modularly. In Vellum, these events are things like the state of the local and global environments, memory, as well as exceptional conditions like undefined behavior, and so forth. In this particular diagram, different types of events are seen as different colors of boxes. And events in our semantics are initially abstract, and we consider every possible interpretation that an event may have, which leads to the branching structure that you see in the diagram. Events are given specific meaning through event handlers. Interpreting events removes them from the tree and gives us a specific structure for the event, which collapses the branching structure of the interaction tree. Here, the orange events have been interpreted, and afterwards we have a more refined understanding of the behavior because the handler told us what the orange events actually meant. So for instance, these events could be representing loads and stores from local variables, and in that case, before handling the local events, you would only know that some value was loaded from a variable x, for instance. But after handling the local events, you would know the specific value x had at that point in the execution, and the value will no longer be abstract. Notably, some of our events, like memory allocations and also the handling of undef values, are non-deterministic. When handling non-deterministic events, instead of refining our interaction tree, we get a set of possible interaction trees for each possible non-deterministic choice. In Rock, we use prop to represent these sets. And using this, we can capture every possible execution that an LLVM-IR program can have. So for instance, we collect executions for every possible way that allocations can be arranged in memory, which is something that can change the behavior of a program. Capturing all of this non-determinism is important. It's necessary to accurately model LLVM semantics, and it grants additional flexibility for optimizations. So putting this all together, we get an end-to-end specification of an LLVM-IR program. This specification is a set which defines all of the allowed behaviors for the program under these semantics. Furthermore, we've also have these verified refinement relations between each layer of interpretation, so between each layer of handling of events. And using these refinements, we can prove behavioral equivalence of programs while leaving certain events abstract, which allows us to ignore things like the particular implementation of memory if it's not relevant. So Vellum currently supports a large subset of the sequential LLVM-IR. If you compile a C program to LLVM-IR, there's a very good chance that we support all of the LLVM features that it uses, except for some specific library functions like operating system things. Vellum has a rich memory model that we published at the previous ICFP that should allow us to verify optimization passes, even in the presence of troublesome low-level memory operations like casts between pointers and integers. And finally, we have a nice interpreter which supports features like printf and command line arguments on LLVM programs, which is useful for debugging. But this also allows Vellum to be used in testing frameworks like CSmith and YARPGen, as well as our own GenLLVM, which generate random LLVM-IR programs using QuickCheck. So Vellum is a large project. It's under very active development. There's about 50,000 lines of spec and 100,000 lines of proof, according to a WC tool that we found for Rock. A lot of these lines of code are actually in the refinement relations established for the new memory model. And for a sense of the scale and complexity of the proof terms, the VO files total about 500 megabytes, and when gzip, they're about half the size. So throughout this process, one thing that we can't deny is that Rock has been invaluable for understanding the semantics of LLVM at a deep level. Formalization really forces us to address many of the edge cases of the language when we're writing the formal spec. And so this is just a non-exhaustive list of some of the edge cases that have popped up during the development of this semantics. Some of these cases we were able to test for and find miscompilations in Clang, and some issues like address guessing are quite subtle but impact our ability to formally justify optimization passes. At the end of the day, formal specifications demand clarifications to the language specifications, and it keeps us honest. So one example of a small subtlety that came up when we were verifying a compiler for the Helix project, which targeted the Vellum IR, I guess, is so there's two aspects in the informal language reference that lead to a mildly awkward situation. So langref states that we can allocate size 0 objects in memory, but it also states that the pointer that you get back may not be unique. It might be shared amongst other allocations. Langref also states that loading from an uninitialized region of memory should always give undef back. This raises some questions about whether loads of size 0 types always like return undef. So like in this case, do I always get undef back when loading an uninitialized p pointer here? Or if the p pointer is shared with another allocation, does that, and that allocation was initialized, does that count as initializing this variable and I wouldn't get undef back? It's a little like fuzzy. And this case is a bit silly because size 0 values don't store any information, but we had to consider these kind of edge cases when we were verifying the Helix compiler. And ultimately, formalization brings these kinds of subtle issues to light, and similar problems can cause miscompilations. So now we're going to discuss our experience with Rock on such a large project. We don't have much time, but we're hoping to share some points where Rock shines and some struggles that we've had. So Vellum's a large project, and Rock holds up impressively well. But we've, of course, run into some issues. Some of these are well-known things that sounds like are getting addressed, which is great. The Rock standard library is a little sparse and can be a little light on lemmas. It's also, the standard library also has some performance issues. There's non-tail recursive functions can be pretty common, for instance, which can cause issues with extraction. Compilation time for our project has been an issue. Some of this is certainly my fault, but we've also encountered some bad interactions between Rock features. For instance, using the program fixed point mechanism within a module type ends up generating a bunch of obligations which show up in that module type, which can greatly increase compilation time. Whoops. Rock also has a lot of constraints in order to avoid inconsistencies. And this is a big strength of Rock, of course, but sometimes this leads to tricky situations in longer proofs, which we'll discuss next. So let's just briefly talk about one of the issues that we encountered in the development of Vellum, where Rock's constraints kind of got in the way a little bit. So the particular details of this example aren't super important, and there's a more complete example at that GitHub repo there if somebody wants to tell me how to do this better. But the gist of it is that the new memory model that we published added a lot of non-determinism to Vellum, which added existentials to our refinement relations. And so we ended up with a lot of goals that ended up looking vaguely like this. Ultimately, juggling all of the constraints on co-induction and large elimination of prop and type and so forth proved challenging for the proofs that we wanted to do. We can't use co-induction to invert the relation R because A and B, the relation R between A and B because existentials are inductive, and Rock reasonably prevents you from eliminating a co-inductive to construct an inductive type. But even if we just wanted to construct A2 itself, which is an I tree, which is co-inductive, we're not able to do that because we can't extract information from the relation R because R is a prop and A2 is an I tree, which is in type. And the constraints on large elimination of prop into type disallow this. Maybe this is preventing me from doing something unreasonable, and I don't understand it well enough. But in this particular situation, I think it should be OK, because the type that I'm constructing is just going to be shoved into an existential, which is in prop in the first place. We managed to work around this issue, but the proof ended up being more complex as a result, because we had to reconstruct some of the information that we needed from the equivalent relation in our work. But overall, Rock has enabled the Vellum project, and we're very impressed with what it can do most of the time. Rock's logic is incredibly rich, and certain aspects of extraction are surprisingly robust in practice, even if it's a little buggy sometimes and we have to patch it up with Perl. Now Gary is going to take over and discuss some of the approaches to testing the Vellum project.
All right. Hello? Can you? All right. So So now that we have a large verified interpreter that is proven to be correct and can evaluate LVM programs, one key question is how do we ensure that the interpreter adheres to the LVM IR's informal specifications? For us, testing is the way to go. In Vellum, we built a large unit test suites that we both develop in-house as well as using the test suites from Alive2. More importantly, we are also using differential testing, test real-world implementations to our implementations to find bugs. Compiler differential testing is not a new topic, and there are some well-known state-of-the-art generation frameworks like CSmith and YARPGen that we are comparing ourselves with. So if we look back to the graphic presentation of Vellum structure, using iTree, we get a verified interpreter for LVM programs, and we can run programs like this factorial programs through it. We can compare the behaviors of LVM program run with our interpreter with the behavior under the Klein compiler. If there is any difference in the behavior, that would indicate a bug somewhere. To increase coverage, we will generate many random LVM IR programs, feeding them into both Vellum interpreter and Klein compiler and see if they differ. Generating LVM IR program is tricky. Specifically, we need to maintain some property for the programs that we are generating. Most importantly, they should be deterministic so that we can easily compare the output to identify potential discrepancies. We also want our generated programs to be varied and exercise a large subset of the LVM IR syntax. To this end, we built a tool called GenLVM for generating random LVM IR programs on top of the generator monad provided by QuickCheck. We also include other features like early terminations and a context-aware metadata system for tracking various properties of the generated variables, such as their types and whether or not they are derived from a pointer for reasons we will soon get into. Due to time constraint, here we briefly show the generation strategy of GenLVM. This is fairly complicated and involves several mutual recursive functions to ensure expressiveness as well as ensuring well-formedness, for instance, when generating loops. As an example of something that is tricky to generate, consider the example of naively generating into pointer cast from an arbitrary integer. Here we cast an arbitrary integer, in this case 123, into a pointer, which isn't necessarily allocated, so that the program can exhibit undefined behaviors. CSmith and YARPGen both avoid into pointer casts, partly because of this reason. In this case, we need some metadata about how the integer is derived in order to know whether we can cast it into a pointer and read the value pointing to it safely and deterministically. There are many state-of-the-art generators, so a natural question is why don't we just use one of them? Well, CSmith and YARPGen actually generate C programs that have to be compiled down to LVM, and we think that this process can introduce bias in the generated LVM code, and some instructions may not be well exercised. We've evaluated this hypothesis in GenLVM as a whole by generating 10,000 programs using each of these generators and comparing the distribution of the LVM syntax use. We've noticed that we've generated a wider variety of instructions, especially in aggregate data as well as pointer to integer casts. And we've also noticed that our interpreter is fairly efficient. We've also discovered various discrepancies between Klein and Vellum using GenLVM. Here we are showing an actual bug of Klein that we found using GenLVM. It's an off by one extract value error. So this code effectively zero initialized a 32-bit pack struct that contains a vector and an integer, and then return the last byte as shown graphically on the right. Because all of the bytes are 0 and we are reading from the last byte, we would expect the return value to be 0. This is the result given by Vellum. However, the executable generated by Klein will output 46 or some random value. When compile this code down to RISC-V, we've discovered that extract value when working with a pack struct with vector can trigger an off by 1 error. That is, instead of loading a byte from the stack pointer offset by 15 as what is done in the pack struct with array. The generated assembly code is loading a byte from the offset by 16. As you can see graphically, this is incorrect. In contrast, extract value is being compiled correctly when dealing with pack struct with array. So overall, we had a really great experience with Rock Proof Assistant, and that really helps formalizing complex system. Co-induction and interaction trees are helpful in defining some semantics, and also Rock's ability to extract executable allows for differential testing, which is essential for debugging and finding bugs in Vellum, Clang, and language reference. These takeaways make Vellum a useful platform for formally understanding LLVM-IR semantics. And these are some future works. And if you want to learn more, feel free to visit our GitHub repo or chat with us. Thank you.
Okay, we're running a bit behind, but we have time for a couple questions. So I have one while we move back there. You said it was relatively easy to add new intrinsics. What do you mean by relatively easy?
You basically just like there's a couple of ways that we kind of add new like intrinsics or instructions. You basically just add like a kind of Coq definition for it, and it's relatively easy in the sense that with the new memory model stuff, you have to do one like proof that like this like infinite memory model that we have is refined by a finite memory version of it, and overall it's pretty easy.
Thanks for the talk. I was wondering, you talked a lot about that this is a platform for understanding like the semantics of LLVM. I'm also wondering, how much do you like not just think about the semantics, but also about the optimizations and like the things that LLVM is doing? Like, do you have a plan? Like, at some point, you want to have like all the optimizations in LLVM verified in ValVM, or like, are you working towards that, or in general, what
yeah, so the next steps are kind of like, we built all this memory model stuff so that we could verify certain kinds of optimizations, and we're hoping to use that to prove optimizations like mem to reg and stuff. So we currently don't have any verified optimization passes in full, but that's kind of the next step, yeah.
Time for one more question.
I just have a question, since you seem to use I-trees with non-determinism a lot, and you didn't talk at all about C-trees. Is it something you have looked at? Is there a problem with C-trees that don't make them work for you?
We're definitely considering migrating stuff over to C-trees is the answer. This work was kind of done in parallel with the C-trees work, and we're working on merging stuff.
Just go for it.
And I was wondering about the connection between your work and Alive. Like, is it something you just check whether you say the same thing than Alive at the end, or did you use Alive to design your rock semantic?
So in the Alive project, I think they've generated a lot of like test cases, and some of them are deterministic, and we kind of basically run the deterministic test cases from the Alive.
All right, let's thank the speakers once again. Now it's time for lunch. We'll see everyone back All right. But
Can we test your
Test.
all right, welcome back everyone to the third session of CoqPL. So our first talk is going to be from Yihan. She's going to be talking about some work she did during her summer internship at Lawrence Livermore. And just as an advertisement, she's graduating. She's going to be looking for PhD applications, or she's on the market, or whatever the phrase is right now. So take it away, Yihan.
Thank you. Hello, everyone. I usually go by Yuki, and I'm an undergrad from Humboldt College. Today, I'll present our work to verify linear algebra programs through equivalence. This work was done at Lawrence Livermore National Lab as a summer project in collaboration with Mohit, John, Matt, and Ignacio. They were all from Lawrence Livermore National Lab. Right. Scientific computing is changing fast. We're seeing big shifts in how computations are done, driven by new trends in hardwares. For example, we're seeing data compression floating point formats to deal with the cost of moving data around. And that was a huge bottleneck in traditional computing. We're also seeing a lot more reduced and mixed precision formats, especially in things like machine learning. And on top of that, there is a big push toward parallelizing computations on GPUs and FPGAs, along with a shift toward heterogeneous architectures. And those changes in scientific computing means that we need a new generation of numerical algorithms. But here comes a challenge. For the case where the new algorithms are a variance of the existing algorithms, how do we make sure that those new variants are correct and safe to deploy? And that's the key question that we need to address as we move forward. So the solution to this question is to prove the equivalence between the new variants and its classical counterpart. There are a lot of classical stuff that can be served as a ground truth of the correctness of the new variants. And the recent work published at PLDI last year proved the equivalence between dense matrix vector product and sparse matrix vector product with different sparse matrix representations. So inspired by this work, we aim to prove equivalence between variants of a fundamental orthogonalization algorithms. It's the Gram-Schmidt algorithm. The Gram-Schmidt algorithm has two variants, the classical one and modified one, where the modified one is more numerically stable. We picked to prove the orthogonalization algorithm because it is very fundamental in linear algebra, and it has a lot of applications. It's very important in machine learning, such as in optimization and regularization. Some other applications include cryptography, where they use the algorithms to orthogonalize the basis of a lattice for better efficiency and security. It's also being used in signal processing and noise reduction. So with the goal of establishing program equivalence between the classical Gram-Schmidt and the modified Gram-Schmidt, we proposed those three research contributions. We extended the MathComp library in Coq to include basic linear algebra theorems, and then we used this extended linear algebra libraries to prove the properties of Gram-Schmidt algorithms. And we finished the proof of the classical Gram-Schmidt by the time of this presentation. Furthermore, the library is a building block toward floating point reasoning and error analysis. So what exactly is the Gram-Schmidt algorithms? Well, it takes in a set of finite linearly independent vectors in some space Rn, where we call it V1 through Vk here, and then it outputs a orthogonal set that span the same subspace as the input set. And right here, we use the letter U to denote the output. So in other words, it creates a orthogonal basis from the input set. So we can take 2 dimensions, for example. We can see that V1 and V2 over here are the input vectors. They are linearly independent. And then we output vector U1 and U2, and we can see that they span the same space and they are orthogonal to each other. The algorithm accomplished this using the idea of projection. So by projecting V2 onto V1, it breaks up V2 into 2 components, and the component that is perpendicular to V1 is our result vector U2. And in math, projection is defined as some operation of dot product. So going back, Gram-Schmidt has 2 variants, where the classical one is very well defined in linear algebra, and you can find it in almost every linear algebra textbook. So the computer scientists took the classical version and then coded up and see that it is numerically unstable in floating points because of the running errors. Therefore, the computer scientists developed a new version called the modified Gram-Schmidt to reduce the errors. And we can see that right here. The modified Gram-Schmidt uses another iteration of projections of vectors to reduce the running errors. And then I can talk through the math a little bit more details. So in in classical Gram-Schmitz, we take each vector one at a time and make it orthogonal to all the previous vectors. However, in modified Gram-Schmitz, we take each vector and modify all the forthcoming vector to be orthogonal to it. If we could take 3 dimension, for example, here we want to project V3 onto U1 and U2 to come up with the resultant vector U3. And then it's just simply subtracting the component that is perpendicular to V3, U1 and U2 right there. And then we're in modified Gram-Schmitz, we first project V3 onto U1 to create an intermediate vector right here, and then project this intermediate vector onto U2. So by iteratively projecting the vectors onto the already orthogonalized vectors, it could reduce the running errors and then make it more numerically stable. So we can look at evidence for stability. Here is a study at UPenn. The orthogonality error was calculated for both the classical and modified version. We can see that as dimension k goes up, the error for classical Gram-Schmitz, which is shown in this middle column right here, quickly diverges away from 0. Well, the modified Gram-Schmitz stays, the error of modified Gram-Schmitz stays relatively low. So with the goal of proving their equivalence, we also want to focus on stability and convergence. However, existing work doesn't fully address this. Where in Isabel Hall and Lin, they both only consider the classical version and does not consider numerical stability. Furthermore, in Lin, which is widely used to magnetize math, it uses a non-computable definition of classical Gram-Schmitz. Thus, we cannot extend the result to actual programs. So our work tackles this challenge by formalizing Gram-Schmitz and keep in mind the numerical properties such as stability, numerical convergence, and flows in the long run. So next, let's go to some technical details of how we actually magnetized Gram-Schmitz. Looking back at the definitions, we certainly need some definitions of vectors and linearly independence, orthogonality, and the idea of vectors spanning some space. The process of Gram-Schmitz also requires us with the definition of projections and dot products. We use the mathematical component library, aka MathComp, in Coq to develop the implementation. And MathComp has 2 sublibraries called vectors and matrix that's really helpful in doing this. Those libraries provide a lot of low-level definitions such as vectors and linear independence. However, it lacks definition of dot product and thus orthogonality. It also does not have higher-level theorems such as the basis theorem that are required to prove the correctness of Gram-Schmitz. Given this situation, we used MathComp to build toward a comprehensive linear algebra library that can help with the proof of Gram-Schmitz. The library starts with our own definition of vectors, which is defined as a column matrix, and then we define dot product and projections in the usual mathematical way. I don't have the time to go over our entire library, but here shows the dependency graph of the properties that was proved in the library. Here you can see that we proved the distributive property of dot product, some projection properties, and we used those more fundamental lemmas to prove more involved theorems such as orthogonal decomposition theorem and the basis theorem. And there's one theorem that I kind of want to walk over this time is this theorem called products ortho, which is more formally known as the orthogonal decomposition theorem. So here's what the theorem states. It's very mathy, so I want to walk through the definition of the theorems. So we have a vector A and a set of vectors U0 to UN-1 in some space Rn. We conclude that A minus the projection of A onto all those V's, the result would be orthogonal to all the V's. We can imagine this as breaking up the vector A into components that is perpendicular to all the V's, and then by subtracting from those components, the leftovers must be perpendicular or orthogonal to the V's. And an equivalent Coq translation of the theorem is shown in the middle right there. And notice that here I have a little trick. Instead of saying that for any set of V's, the result hold, I made it stronger by saying, oh, let's fix the V's to be V0 to Vn-1. And then we consider a subset of them by only considering the V0s to Vk-1, where k is less than or equal to m. I do this trick to better fit this use case in later on proving Gram-Schmitz. And if the k just equals to m, then this is exactly same as orthogonal decomposition theorem in the Max textbook. And the proof of these properties requires dot product and projections, which are missing from the MathComp library. But with our newly created linear algebra library, we were able to successfully complete this proof. And I'm happy to go through the details later if anyone is interested. And this theorem was also added to our library later on after the theorem is proved to prove the correctness of Gram-Schmidt. So after we create the library, we're now ready to prove the correctness of classical Gram-Schmidt. Here shows the dependency graph of proving the correctness of Gram-Schmidt, and we see that it uses a lot of properties established in our linear algebra library, and all those arrows pointing to is a lemma that's unique to our own library. And let me zoom in on this lemma right here in the middle. This is called non-zero result vector helper. I named it myself, and this is the key helper lemma to help us develop the correctness of Gram-Schmidt. And here's what it states. It also gets really messy. So let me walk through. So let this set of v's, v0 to vm minus 1, be some vectors in Rn, and they are linearly independent. So they are the input to our Gram-Schmidt algorithms. Let all the u's, u0 to vm minus 1, be the result of Gram-Schmidt. And we conclude three things. First is that all the u's, all the result vectors are non-zero, that's the first one, and they are pairwise orthogonal, that's the second one. And furthermore, the third one is that all the v's span the same space as all the u's. This almost comes directly from the definition of Gram-Schmidt in classical math textbooks. I added the result of all of them being non-zero as an additional conclusion to help me reason about this proof. And the inductive hypothesis of this proof would be that we assume for a certain k that the first k of all the u's holds for these properties. And then for the inductive step, we want to prove that it holds for k plus 1 as well. So to prove this inductive goals, we have three parts that we need to prove. Let's see. Go. Okay. First is that the k plus 1 vector mean the uk is non-zero and that it is orthogonal to all the previous u's and that it spans the same subspace as the first k vector, as the first k plus 1 vectors in the input set. So to prove the first one, that uk is not zero, I break it up into, I've expanded out into its formulas, and then to prove this, I used both the lemmas in our own library and also some already established quite good lemmas in MathComp. And to prove the second part, I used orthogonal decomposition theorem, which is the one that we just saw in the previous slides. And for the third one, we actually need to use the basis theorem right here. So yeah, we're able to successfully complete the correctness of classical Gram-Schmidt using our own library, and we are in the process of proving the correctness of modified Gram-Schmidt. A lot of helper lemmas in the classical Gram-Schmidt can be used here, and there is an additional lemma that is unique to modified Gram-Schmidt is already proved on pen and paper. This basically saying something about, properties about this intermediate vectors that is unique to Gram-Schmidt. And last but not least, we could use the orthogonal decomposition theorems together to complete the proof of modified Gram-Schmidt. And the proof structure of those two versions essentially established so that the equivalence one will be very simple by just doing an induction on the number of input vectors. And after we do that, we could successfully close the exact equivalence of those two algorithms in real numbers. We're imagining our work to be contributed directly into the MathComp library, mainly in the vector library, because we use a very similar definition of vectors. And we hope that our library could be established for proving other basic linear algebra theorems that utilize projections or orthogonality. For example, people can use our library to mechanize some ODE solving techniques that heavily relies on linear algebra. And our library can also help with the mechanization of QR decomposition, which is an application of Gram-Schmidt algorithms. And for a long-term future work, we're thinking that there could be three possible ways. First, we could reason about floating point programs, and this extension would require first adapting the equality constraints of our lemmas to symbolic bounds, because in real numbers, two vectors being orthogonal meaning their dot product is 0, but then that's not true in floating points because of running errors. And second, we could extend our equivalence result to reasoning about low-level HPC programs by using separation logic such as Iris. And our final direction could be extending recent mechanized relational equivalence framework such as LGTM with support for floating points and proof rules for common linear algebras to include modular reasoning. And that would significantly automate the process of constructing floating point error bounds. So in conclusion, we extend our MathComp library to include some linear algebra theorems, which we later on used it to prove the correctness of Gram-Schmitz, and we expect it to be extended to handle floating points and error reasonings. I'm very grateful of our results so far, but the process is not very smooth. First of all, it might be a surprise for you all, but mechanizing math is actually quite hard because of a lot of missing pieces in the libraries. In addition, formalizing software is also challenging because essentially missing those building blocks that's missing from the library enable us to create our own new library of linear algebras. And so Gram-Schmitz is a very fundamental algorithm in linear algebra, but we expect it to be more complex when proving more complex and more involved algebras. And as a learner of Coq myself, I spend a lot of time trying to prove some common sense results. Therefore, I ask for more automated theorem proving tools. And I use LLMs a lot during my proving process, and I'm happy to explore ways of how LLMs could help in automating theorem proving. Last but not least, I have mixed feelings about floats, but it is because it is not as exact as reals. But I'm grateful to have the Coq library called Flock and MathComp to help me reason about floats and reals in Coq. Thank you for your time, and I'm happy to take any questions.
We have plenty of time for questions. Is there any questions in the audience? We got one right over here.
Thanks. Is that working?
Oh, it was working.
Yeah.
Now it's not.
I'll just. How much of the geometry depends on?
Okay, yeah, just to repeat, the question is asking whether how much of the proof relies on the definition or the representation of vectors. Is that right? Yeah, so we define vectors in a pretty standard way, I would say, is being defined as column matrices. Right here is a column vector. And that by defining it that way, we could use the matrix library in MathComp and also the vector library in MathComp to reason. So I would say the proofs definitely relies on this representation. I would say this representation is pretty standard. Yeah. In matrices, I don't remember it to be iteratively defined. I think, yeah. Yeah, I feel like because there's a lot of lemmas in vectors and in matrix that we can directly use, so I didn't have, it's not heavily relies on how it is defined because there's already many lemmas help me to iterate with the representation. Yeah.
I'm wondering why you chose to base your linear algebra on the matrices as opposed to the vector library, which is basis independent.
Sorry, could you repeat your question?
So there are basically two linear algebra libraries in MathComp. One which is representation dependent, which are the matrices, and one which is basis independent, which is the vector library.
Yeah.
I'm curious why you chose to work with the matrix library rather than
the
vector library, which is a little more abstract.
Yeah, we actually use a lot of lemmas established in the vector library. We use it a lot. But then one reason that we didn't use it because there is no definition of dot product in the libraries. I mean, it is like
you could add it, right?
It's like implicitly defined used by like the transpose of one vector times the other vector in the matrix library. But then because it doesn't have the definition of orthogonality, which heavily depends on dot product, so we didn't really use the vector library. And also vector library does.
I understand, but you could have built on top of it as opposed to trying to hook yourself to matrices, which are a little more lower level.
I think the vectors defined in the vector library uses the column matrix representation.
Internally, but it doesn't.
Yeah.
The interface doesn't expose it.
Right. Yeah. I mean,
there's actually an example of this in the MathComp library, but sort of further down. The theory of characters actually develops the whole theory of dot product and orthogonality. It just does it only for class functions because we're kind of goal oriented.
Right.
You could have used that as a basis for rolling out your own while being staying above the layer of the matrix.
Right. I think we could talk later.
Yeah, maybe we can take this offline.
I'm curious about that library.
The next speaker, is the next speaker in the room? Yeah, can you come get set up? We have time for maybe one more quick question.
Oh.
Or not? In that case, let's thank Yuki once again. And so our next speaker is going to be Runchin, and he's going to be talking about verified differential operators in Rock. Eventually.
So maybe I just use it in this way. Okay. Thank you for introduction. I'm Ren Qing. I'm a PhD student from the Johannes Gutenberg University Mainz, and today I want to present a framework for modeling and verifying differential operators in the Thorium pool Rock. And this is a joint work done with my PhD advisor Sebastian Edweg. And so at the beginning, I would like to briefly introduce incremental computing, which is the context and the background of our framework. So incremental computing mainly investigates how to efficiently update a program's output based when the input constantly changes. So here is a small diagram showing how a typical incremental program works. Oh, sorry. Sorry. So when there is the input reached an incremental program, and when it's the first input, it will just work normally as a normal program, just translating the input to the output. But after that, if there's a change to the input, the incremental program will not rerun the whole program from scratch. Instead, it will try to efficiently update the output by analyzing the mathematical properties of the structures of programs. And this process just repeats every time the input changes. And in the past decades, there are numerous studies have shown that incremental computing in some cases can be asymptotically faster in theory and gain 10x to 10,000x speedups in practice. So how do we implement incremental computations? There are typically two ways. The first way is called selective recomputing, and the basic idea of selective recomputing is try to reuse the previous subcomputation results when possible. In other words, it just tries to incrementalize the programs by analyzing the dependency graph. The advantage of this selective recomputing approach is they are purely automatic and can be applied to incrementalize any programs. But it also has a fundamental limitation, which is they don't have a notion of change, only a notion of change. So basically, there are only two types of changes in selective recomputing approaches, which is either no change or replace change. And the consequence is that they cannot incrementalize programs by the algebraic properties of changes. And here is a tiny example. Suppose we want to incrementally compute the sum of a list of integers using folding. Here, if we use the selective recomputing approach, it will first build a dependency graph of the computation, which is sum 2 to 5 relies on sum to 2, and sum to 2 relies on sum 2. I use the yellow color to denote the newly computed results in incremental computation, as this is just the first computation, so everything is newly computed. And after that, so consider we insert at 0 at the index 1. So the input becomes 2025. So now what happens, the dependency graph will be modified. As we only insert at the first computation result, sum 2 will not be affected because it is right before the insertion place. But after that, all of the computation relies on the newly inserted elements, which results in many wasteful computation because we know that actually the integers form a commutative group, so we actually don't have to care about the order of computation. So we only need to plus the original results with the newly inserted elements. So to complement this approach, another approach for incremental computation is called differential updating. And the basic idea of differential updating is we just translate the input change descriptors into output change descriptors. We are changing the differential operators. So we usually use normal operator to refer to the function that maps the input and output, and the differential operators just maps the input change to the output change. Here is a small example of differential updating programs, which is just a network of differential operators. And so we can revisit the previous example via the differential updating approach. So in order to define a differential operator for sum, we first need to check its type, which maps a list of integers to an integer. So we need to define changes on the list and the integer type. Suppose there are two types of change to a list, which is either insertion list or deletion. Insert some element at some certain index in the list, or delete elements in some index at some certain index. And the output, the change to the integer just plus it with another integer. With this change, we can define a differential operator for sum. And so if we just insert something to the list, I think so we only need to plus we only need to output a change that plus the original results with k. In the other case, we plus it with negative k because it is correct because we know that the integer adds is commutative and its time complexity reduced to constant time. So apparently the differential updating approach is very effective, but it also has some limitations which prevent it to apply into more fields. And there are two limitations. The first limitation is it's very hard to develop correct and efficient differential operators, as I can show you later. And the second limitation is currently there is no general PL framework supports composing differential operators with language constructs like if-then-else recursion, to the best of my knowledge. So our work just wants to tackle the first limitation and to capture the essence of the correct and efficient differential operators. So in order to do that, we define a framework for modeling and verifying differential operators. When we design this framework, we want to ensure that we want to model differential operators that at least meet these two requirements. The first one is probably correct. It's very important, and because we want to do some drop-in replacement for the non-incremental ones for incrementalizer programs. And the second requirement is it must be very efficient, which is the root of asymptotic speedups and the motivation of using incremental computation. And the second requirement also requires our framework to be expressive enough to model these efficient operators. So now let's just dive into the details of our framework. The first thing I want to introduce is change structure, which defines how change can change, which defines how data can be changed. And it contains 4 fields. The T means the type of the value, and delta T means the type of the change. And patch is the function that patch a change to a value and get a new value. And as we know that sometimes the value cannot be changed in an arbitrary way. For example, natural numbers cannot be subtracted from a bigger one. So we use a binary relation VC to denote the value, to specify the value change to a value. And we use the notation O plus to denote the patch function in the following. And here is a small example of change structure on natural numbers. We can first define the change type, which is either add a natural number or subtract a natural number. And when we subtract a natural number, we should be careful because the subtract number cannot be greater than the original one. So we can define the natural numbers change structure in this way. And here is a very interesting question. So what we want to get from VC, which means that, as we can see in the change structure, VC is nothing but a custom binary relation. But what we want to do with VC is to prevent we doing arbitrary changes on the values. So how do we just visualize VC using the Coq language, ROC language? And this stuck me for a while. So after that, I just realized what we want VC to do is to make the changes invertible. I specify it with another type class. So we first define an undo operation, which means that we undo a change to a value. And we just can specify a good VC should capture that a valid change can undo update value to the original value. So TO plus delta T minus delta T equals to T. This captures most of how the good VC looks like, and I feel it's really cute to share with you. So we can also build some higher order change structures. For example, if we have also already defined a change structure on A and delta A, we can also define a change structure which apply a sequence of valid changes to a value of type A. So after that, let's move to the interface of stateless differential operators, which is the most simple form of the differential operators. We specify its signature as a module type, and the parameter AB delta A delta B just means the input type, input change type, output change type, and we require that CA and CB are the input change structure and the output change structure. And the parameter f is the original operator, and the delta f is the stateless differential operator. Just maps the input change, the output change. And we capture the correctness of this delta f through two axioms. The first one is if the input change is valid with the input, the output change should also be valid with the original output. The second one is which we usually call as from scratch consistency, which means that if the input change is valid to the value, then we doing recomputation f of x o plus delta x should be equal to update the original output with output change. So here is a natural question. As we can see that in all of the axioms, we all add a precondition for the input change. So we may have the question that is it possible to develop a very smart delta f which can work correctly without VC? Well, actually the answer is no. Because, for example, this is a very simple example. Suppose we have a inc operator just add a natural number by 1. So its differential form is just an identity function you may consider. And here is the fact that if we do a invalid change sub 2 to 1, then it will be I equal to inc 1 o plus delta inc sub 2. The deeper reason is that we're actually doing ambiguous things on the left-hand side, and but the stateless differential operator is not aware of this fact. So this is the first takeaway I learned from this formalization, which is the valid condition is crucial for developing correct differential operators. And we can also prove that it's very easy to prove that stateless differential operators can work on valid input sequential changes. And here are some examples we formalized using our framework, which are some very known facts, such as the selection and union relational algebra operator are all stateless. That's why database have a lot of incremental computing works. And so as we become more and more familiar with with the differential operators. So why not we do a small exercise together to define a differential operator for the trim right function, which is a string function that will remove all of the rightmost white spaces from a string. For example, trim right white space, CoqPL white space will delete the right white space. So suppose we only consider three kind of changes for the string, which is append a character or prepend a character or no change. And now let's do these small exercises together. So the first case is what will be the output change if we append a white space to the original input? Because I think the trim right will remove the rightmost white spaces. So adding a white space on the right will trigger no output change. So now let's consider what if we append a non-white space character C to the original input. Yes, because of the time constraint, I just continue. So someone might think that at C, the non-white space character and if it will be added into the tail. So maybe the output change is append C, which is actually not, because when we add C to the tail, all of the previously trimmed white spaces becomes not the rightmost white spaces. So we actually need to append both of the previously trimmed white spaces and the newly inserted appended character. So the next case is prepend white space. So as the trim right only handle the white spaces on the right-hand side, should it naturally be the output change is prepend white space? Well, actually not again, because we forget the case that if the original string only contains white spaces, then the prepend white space will not get any output change because the output is still empty string. And in the other case, it's just prepend white space. So the last case is prepend C, which if the C is a non-white space character, the output change should be prepend C. I just want to use this example to show that sometimes the differential operators are stateful. And for example, for the trim right, we need to maintain two states, which is the number of the trimmed white space and the flag indicating if the entire string was white space. So these two states are crucial for performance and both for correctness. So this is the second takeaway. From this example, we can find that implementing efficient differential operators sometimes require us to maintain custom states, and these custom states sometimes can not be the previously sub-computation results. So with all of this knowledge in mind, let's see the signature of stateful differential operators. So the first part is the same as the stateless one, just specify the input and output change structure. And okay, as we add state to the differential operators, so we use st to denote the type of the state. And what is really cute about this formalization is we realize that we can also add a change structure on the state to simulate the state update functions, because every time we apply this operator, the state has to be updated, and the state update function actually has the same type as the PySh function. So we can just abstract it as a change structure, and with the state type we can define the delta f as a stateful computation. And here it comes to the correctness of delta f. In order to do that, we specify a binary relation between the input and state as a invariant and capture the correctness of delta f under the condition that not only the input change should be valid, but also the state should be correct and maintains the invariant. And the last part is about we not only want the stateful operator works correctly for once, but also works for a sequence of changes. So we just define an initialize function that transforms the original input to the state and impose that it should work correctly from the initial state to every updated state. Okay, we successfully proved that the stateful differential operators can also work on valid input changes sequential valid input sequential changes correctly. So we also do some case studies we successfully use the stateful differential operator's signature to model two very efficient incremental differential operators, existing differential operators. For example, the join operator can be incremental, can be incrementalized very efficiently via the join index, which is actually widely used in current database implementation. And another example is incremental aggregation, which we use the aggregation tree to maintain the state, to add the state. The incremental aggregation are widely used in the implementation of incremental data log servers. So here's the conclusion. We formalized an open source framework for developing and verifying efficient differential operators in ROC. And we successfully use our framework to model existing and novel differential operators. And our future work includes we'll start to consider how to comprise sequential changes, and ultimately we want to develop a standard library for differential operators for the most common data types. Okay, thank you for your attention. I'm happy for any questions.
We have time for questions. Any questions from the audience? Just keep talking.
Hello? Okay, I think it works. So in your slides about invertibility, I assume not all patch has invertible undo, right? So it seems to me you actually want to generalize this definition to like something like taking the patch and the final result. You might want to have like an undo that returns like a set of the possible
change descriptors
values, right? So I'm wondering, do you run into any issues because of this restriction, or is that not?
Yeah, there is a very simple example to show the VC is not that general, which is just a replace change. For example, if we only define the replace change as replace a new value, then it is not invertible. But we can also define a VC, because VC is always true. We can always replace the values. In order to define an invertible replace change, we are not only need to specify the newly replaced value, but the old value. So this is just an example to show why this invertibility not always works, but it just very capture a good shape of VC. So what I actually want to share it here. That's the reason.
Any other questions? So maybe I have one. So this invertible class, does that actually show up anywhere else? Like it seems like this wasn't actually, this class didn't appear in any of your other definitions, in particular your definition of the stateful operator.
Yeah, it does not show anywhere because it just by recent finding about it. But I can also tell you prove that the natural number changes or back changes or sequential changes, they are all invertible under my defined VC. This is VC, which is I see. Yeah.
So maybe one last question while the next speaker sets up.
Hi. Yeah.
Hello?
Hello.
Okay.
Yeah.
You said you have a change structure on the intermediate state used for stateful diff operators. How is that used? Where does that?
Yeah, this is just the starting of a very big incremental computation project. We want to also develop a PL framework that supports stateful differential operators to have a semantics to correctly use them. But this is just ongoing work.
Okay, so you don't currently use the change structure that you've put on the intermediate state for your stateful diff operators?
Oh, sorry, I misunderstand your question. You mean the change structure on the states?
Yes.
Yeah. Okay, I can just yes. Most of the all of the stateful differential operators can define a change structure on states. I just we can just abstract in this way. I abstract the state update function as a change structure, which is because just because their type is the same. So we can always do it. Yeah, when define the yeah.
Okay, thank you.
Okay, let's thank our speaker again. Yeah, the microphone.
Oh, no, sorry.
Yeah. Okay. So our next speaker is going to be telling us about.
So my name is Tarak Ram.
Yes, our next speaker will be telling us about semantic logical relation for session types. So take it away.
Good afternoon, everyone. This is a joint work with Jules, UA, and Stephanie. And just to note that any comments I make in this talk are my own, not representative of the US government, because this is recording, so I need to make this. Okay, so it is not always possible to have contributions on the second slide, but we are lucky. So this is the first mechanization to prove determination of intuitionistic linear logic session types. So let me briefly review what session types are. So session types are like a formalism to describe the communication between two or more parties. And these parties, pairwise, they communicate over a channel. So session types are defined in terms of the sequences of input and output operations, and with each operation indicates the types of the messages. So these types of the messages will become the types of the channel. And session types are expressive enough to allow branching with internal and external choice. And the type of the channel determines the exact order in which data is exchanged between the parties. So what are the channels? Channels connect to communicating parties, and the parties, like usually we call them as client and a provider. You can see the provider to the right-hand side and the client to the left. These parties have a dual behavior and dual types. This property is called duality. So for example, a client sends a message of type int. The corresponding provider will be expecting a message of the same type. The duality is enforced during the by typing rules. And the channels are only known to the client and the provider, hence session types provide communication privacy. Okay, so I will introduce our types. So for arbitrary types, A sub I, we define A1, lolly, A2. So the types are defined in terms of the provider. So you can see that we have the client on the left and the provider on the right. So the type, so this client and provider are communicating over a channel, and the type represents the communication happening over the channel from the perspective of the provider. So this means that A1 lolly A2 means that after the provider receives a message of type A1, the protocol transitions to A2. That means the communication happens of type A2. The message will have type A2. And A1 tensor A2, this means that after the provider sends a message of type A1, the protocol transitions to type A2. And we support branching, internal A1 O plus A2 and A1 ampersand A2. These are like internal choice and external choice. Again, these are with respect to the provider. And then we have end of protocol. It's like a unit type or 1. So I would like to note that the message here can be like a message or a channel reference, but in our setup, it's just a channel reference. So that means that A1 lolly A2 should be considered as after sending a channel reference that the protocol transitions to A2. And now, I will show some examples, some semantics using our tree dynamics introduced by UA. So here we have a provider to the on the top. We can see the client. We can see the client as the root node of a tree. Here the client is running a program case A, Q1, and Q2. So what it means is the client is waiting to hear from the provider. The provider makes a choice, either execute the left branch or the right branch, and sends that communication over the channel A. So here the channel is expecting the type A1 O plus A2. That means the provider can choose either left branch or the right branch. Here, for example, the provider is choosing left branch and continues with process P. Because the provider chooses left branch, the client executes Q1. So this will all steps to the client executing Q1 and the provider executing P, and the communication channel has type A1. And let's look at one more example. Here we have a split and pair. Again, the duality. So what is happening here is the client is splitting the channel A. The provider is giving up the control of channel B to the client. So if this steps to the new state where the client has control of the channel B, but all the channels are referenced locally. That means that the client might already have a channel which is communicating with a different provider, and hence what happens is the client generates a new channel and substitutes that for X1. So here B prime is a new, which is fresh. That means it is not a channel that the client is currently using. Okay, next I talk about the shape of our typing judgment. So the typing judgment is a triple delta P:(C). How to look at it is the P is a provider communicating with the client and using some channel. Like this channel is not necessary here, but we can see that it says delta turnstile P:(X:(C). That means the channel X has type C, and the channel X is used to communicate between the provider P and the client. And delta references the channels, the P acts as the client. So delta is the linear context. This means that delta refers to the children of the process P. It is a linear context. That means that duplication is not allowed. And the linear channel contains finitely many variables with types. And P is a process term. It's like it is one of the terms. It executes one of the terms or sequence of the terms. And C is the session types. You can see that like here P is communicating with its client using the channel with the type C. Okay, so let's look at a couple of typing rules. So here typing rule is just like the same inference rule where the denominator, I mean, I'm a math person, I get this like denominator and numerators are used to this. The denominator is a premise which accounts for the protocol state before message exchange happened. And the numerator, the conclusion, denotes the protocol state after the message has happened. So for example, here you can see that the provider is running a program, pair, and it is communicating with its client with a channel of type A1 tensor A2. And the pair has like a few children, but it has especially one children which is with which it is communicating with the channel Y of type A1. And after the message exchange has happened, we saw in the previous slide, and the pair gives up the control of Y. So the pair, the provider has no longer control of the child which is denoted in the filled circle. So after the message exchange has happened, you can see that the protocol is transitioned into a new state where P has a few children, so because it gave away control of Y, and now the protocol state is transitioned to A2. And here we name this rule as tensor write. Here write refers to that the rule is for the provider. And we have the next, once we saw the right rule, we should see the left rule. The left rule accounts for the protocol state before message exchange happened and after message exchange happened with respect to the client's perspective. So before the message exchange happens, the client is running split. It has only one, like it has a few childs, but prominently it is communicating with one child of type A1 tensor A2. And again, so this is the left rule. So this is tensor left. That means the rule for the client. So this was the protocol before the message exchange happened. And after message exchange happened, we saw that the split will continue with Q, and it will have one more child. So that will be represented here. And before I can introduce our logical relation, I would like to introduce configurations. So configurations, so we are like abstracting all this, the tree structure into configurations. So a configuration, you can see, is like a P as a top process, and mu is like all its children. So here we have P, and mu is like a forest of configurations, which is like all these children. Here, P1, P2, P7 are the providers of the client P. So again, the processors P1, P2, so on, they can be clients, and they can have their own providers. And we represent the circle represents that scenario, which is another configuration sigma 1, and so on. And all these sub-configurations like omega 1 to omega n, they communicate with P along the channels A1, A2, so on. So mu in terms is like a mathematical, it's just a map with a domain, the channel variables are channel symbols here, and more accurately, because I haven't defined symbols, A1 and A2 can be seen as channel variables, and it's a map from channel values to configurations. So it's just like the tensor is like just a fancy way of saying that, okay, it's a union, and it's we are appending it with no particular order. So it's just like a finite map. And the domain is just like the values. Okay, because it's the CoqPL, I would like to show some Coq code. So inductively, we define channel as a symbols and variables. Variables, one can see it as like a strings, and symbols as natural numbers. And processes are proc defines process terms, and during runtime, we substitute the variables with the values. So it means that var will be substituted with the symbols during runtime. Just to differentiate these two, we're calling it rproc. And to formalize the configurations, we use like gmaps from the stdpp library, because Jules Advisor introduced implemented gmaps in Coq, so why not? And I would like to point that using gmaps simplified mechanization to quite a big degree. So if you don't know what GMAP is an efficient implementation of finite maps, and it is generic in types of the keys, which is a huge advantage in this mechanization. I would like to say using GMaps might have reduced our burden to 1/3 or even 1/4. So now I will define logical relation. So our logical relation is unary. It is defined inductively on types. So here a configuration omega is in the term interpretation of type A. What it means is omega multi-steps to omega prime, and omega prime is in the value interpretation of type A. What is value interpretation? Value interpretation says that omega prime cannot step any further. It exhausted all its internal steps. So either it is going to be terminated, or it is waiting for some external change from its client. So without that external change, omega prime stays there forever as it is, or will be terminated. Okay, so value interpretation, we defined it in Coq like this. So here, the term interpretation takes value interpretation as input, and it's defined straightforward. RTC means reflexive transitive closure. The step is like the step function. It means that omega steps, multi-steps to omega prime. And value interpretation we defined inductively. So we match omega with configuration with the top process P and mu, and then we do case analysis on the type A. So for example, if the type A has A1 plus A2, that means that whatever the change, like whatever the choice, either left or right, the new configuration will also be in the term interpretation of corresponding type. And then before we can talk about determination, we need to talk about substitution. Because we are substituting variables with values, we have to do that in a way that it preserves types. The substitution preserves types. So this relation says the same. So here, delta is the variable context, and sigma is the symbol context, and gamma is a map essentially from domain of delta to domain of sigma. But just to make our lives easier, we made it like a total map, which gamma is extended to a map from variables to variables union symbols. So outside domain of delta, gamma is identity. If x is not in domain of delta, gamma of x is just x. And such a way that the substitution preserves the typing relation, which is defined in this commutative diagram. And gamma hat is lifting of gamma to the process terms. So let's look at one example, what termination looks like in our setup. So we start with a well-typed program, delta PC, and we substitute using gamma. We end up with gamma hat P, and then our termination says that gamma hat P multi-steps to some Q. Either Q is going to be close, or it cannot step any further without an external change. So let's look at one example. P is spawn close x dot close. Spawn is spawn's new children. You can see that with using substitution x maps to A, this will be first, the top process is going to be R close, and then the top process spawns another child, R close again, because we are substituting x equal to A, and R close is a runtime process. And these two communicate with over a channel A of type unit, and eventually it will step to R close. And it cannot step any further, so it's just terminated. And in a theorem, we can say that a well-typed program and a well-typed or well-defined substitution, given that all the configuration, all the sub-configurations are in the value interpretation. So I think thinking about this yesterday, I realized that the last condition may not be necessary, but I don't have the time to go back and reprove the theorem, so I kept it as it is. So the last theorem says that each child in the sub tree is well defined, or it is in the term interpretation of the corresponding type. But I think that it is not a necessary condition for termination. So if we have these three conditions, and the runtime process gamma hat P will eventually terminate, or will be stay in a positive state. So the corollary is, if we start with an empty context and the P has an unit type, then the configuration P triangle empty eventually steps to close with empty child. In Coq, we have this mechanization. I thought I don't want to keep an empty slide at the end, so I just hand this. So here, the substitution we defined is just like matching. We can see it's a total function. If x is in domain of gamma, it maps to a symbol. If it is not, it just returns the same. And then subst gamma is like a runtime substitution. It takes close and returns close, and it just goes through each and every variable and iteratively looks up the variables and does the substitution. And gamma closure is just like saying that this commutative diagram. And then fundamental theorem says that if we have a well-typed program and a well-defined substitution with a well-behaved configuration, then eventually the runtime process will be in the value interpretation or will be in a poised state. And with that, I will stop here. And thank you.
We have plenty of time for questions. If anyone has any? Right here.
Can you hear me? Thank you for the talk. Very interesting work. Seems to me like your configuration-based dynamics are heavily based on our ability to generate these rooted trees, which we don't get in the classical setting. So I was wondering if you've given any thought as to how your approach might translate to that.
I don't know, like I see it might translate. I don't know, I'm not qualified to answer the question. My co-author Yue might have some opinions. Yue?
So I'm the co-author of the paper. I dealt with the initial study of the theory. My understanding is the intuitionist setting enforces a tree-like structure that is that may or may not be possible to be recovered in a classical setting. One has to. We imagined using some sort of continuation-based thinking, like try to replicate how you would see a classical system in intuitionistic, like lambda calculus. We did not push that far in terms of our development, but it would be interesting to see this play out if possible.
There any other questions? So I have one, which is probably naive because I'm not a session type guru or anything. So your very first slide, or second slide, was your contribution slide, right? And if memory serves, this was the first proof of something. First mechanization for terminal inventions. Okay. So is the what do I say here? Have there been other proofs of termination for intuitionistic linear logic session types?
I think in theory there are, but like they didn't mechanize.
Okay, so the sort of the cool new bit about this is the mechanization effort,
And mechanization,
right?
and ours is like a semantic logical relation. And most of the prior works, like they use like syntactic logical relation.
Okay.
So we don't like to define logical relation. We don't assume well typedness. Like we don't care whether the configuration is well typed or not. We just it's like we don't, the logical relation is not depending on the well-typedness of the configuration.
So. I get. So if I understand correctly, there's sort of two cool bits here. One is this mechanization. The other is sort of the proof technique, which other people, differs from what other people have done before. Okay.
It's like two things.
Very
Yeah,
cool.
okay.
Do we have any other questions? If not, maybe our next speaker can come up and get set up, and let's thank the speaker again. So, while our next speaker gets set up, I'd just like to note that this is one of our student AV chairs. So all of the successes of this, conferences in terms of, AV working is partially thanks to Jan Paul here. So I think we'll probably just give him a round of applause. His hard efforts.
Thank you. I'm up here and it's not an issue, so that must be.
I've jinxed it, haven't I?
Yeah, this is gonna break now. Okay. Disconnect this. Okay.
Okay.
You can change it. Oh, I see. There were issues. All right,
Shouldn't have
there
said
we go.
anything. I apologize.
Okay, there we go. All right. Okay, so I'll get started. All right, hi everyone. My name is Jan Paul. I'm an undergrad at Cornell, and I'm going to be showing some work I did with my advisor Alwyn at NASA Langley last summer. So this is about software-defined delay-tolerant networks. And to get there, we first have to discuss what a delay-tolerant network is. So delay-tolerant networks are pretty useful for any high-latency disruptive environment. So whether it be trying to communicate via satellites through long distances, like interplanetary distances, or whenever there's any natural disasters, these are going to be pretty useful. So the point of the delay-tolerant network is that we have intermediate nodes that can buffer data for hours or days, hence the delayed aspect of them. And a key thing here, aka the key protocol we want to verify is a bundle protocol. So this resides above the transport layer, and this is what ensures the actual delivery. So now we can look at what are the actual bundle protocols we're going to be working with. So here I'm working with bundle protocol v6 and v7. These are just two bundle protocols that the information I'm working with just deals with. I did not choose them. This is what I was given. There's some slight differences between them, mostly that the bundle protocol v7 has updated block structures and can handle fragmentation differently than the bundle protocol v6, which means that whenever we want to send information from one bundle protocol version to another, as these bundle protocols are going to have different versions when they go from one to the other, we want to make sure that none of the information is lost when having to update the information within these systems. So the main thing we want to make sure here is that the information within these bundle protocols is not incorrect and nothing gets corrupted throughout. So here we have what the information looks like. So now we get into the software-defined delay-tolerant networks. So the software-defined part is just going to be this information. So we have a lower layer Ethernet or an IP header for each packet we want to send through the bundles. And then we actually have the bundle. So the bundle is just the block containing the specific field metadata that includes the version and whatever other data we need. And then we have, we might conditionally rewrite or parse these fields for each bundle protocol. So then, by layering the software-defined network on top, now we have a centralized hierarchical controller. And in this controller, this is when we can get into the programming languages part. So this controller installs something called the match action rules, typically programmed in a network language like P4. And we just want to ensure that these rules don't introduce any packet corruption. So this is a quick simplified sketch. So what we have is that we have each cluster being a controller, and then each node runs a data plane, and this is where the P4 code lives. So the links between clusters might be intermitted, hence the delay, and this is why we have the red dashed line showing the delay tolerant part. And we just want to make sure that within the existing clusters, and then going from one cluster to the other, that this match action pipeline, which is what goes from one cluster to the other, matches the information in a secure way. We want to make sure that this is safe. So there's some basics here. So we can step back from the actual programming languages of P4, and we can just look at general calculus, an abstraction just called the network calculus. So this is pretty well founded. There's a lot of papers that discuss how to formalize network calculus. So this part is pretty straightforward here. So the main two things we want to show here are the bounding queue buildup and latency guarantees. So we have a couple of things here. So we have a cumulative function such that for A of t, this measures the data arrival by time. Then we have a minimal service guarantee via the service curve as well. And then I'll explain what this min plus convolution is doing there in the middle between the A and the beta. And then we also have the min plus convolution. This is just a pipeline composition. So I guess, yeah, okay. All right, so here we get to it. So, so diodes are going to be the core of this network calculus. So we have the O+, which is typically just min. So this is going to reason about aggregate functions like min of A and B to simulate or model bounding. Then we actually have the min plus convolution from the minimal service curve guarantees. So in here, we can just say, so for a server S1 that has a service curve of beta 1 and a server S2 that has a service curve of beta 2, then their cascade has a service curve of B1 O times B2. This is the min plus convolution. And now you can see how it makes sense here with the arrival time and the additional now beta of T insurance. We also have a couple of other things here. So we have the absorbing element, and we also have the identity element. So identity just gives us, so if a stage is no delay, no loss, it doesn't reduce service. And the absorbing element is just to give us information for when the entire pipeline can effectively deliver 0 data. So this gives us a framework for reasoning about the network abstraction. So these are, excuse the badly formatted LaTeX there, but this is how it was simulated in Coq here. So we just have a commutative function at CF1. Here, this is the actual function A of t describing how much data arrived by a time t. Then we also have the non-decrement. So this is just a sketch here for the proof that A of t never decreases as the t time increases. And we also have some proof that A of 0 for a time 0 equals 0. So these are just some basic proofs to be able to give some abstract guarantees about an arbitrary network that would use this calculus. So going forward here, I'm going to skip through the actual description of that, and I'm just going to go to the programming language part. So back to P4. So I was given a match action pipeline, which is an algorithm implemented in P4 that manages the network flow. And what we want to do here now is I have a network calculus that has certain guarantees proved in Coq, but the actual P4 code still doesn't have any guarantees whatsoever, and it doesn't really interact with the calculus I've abstractly defined. So we obviously know that you could mechanize some P4 code, I guess, if you have some way of mechanizing it, but that's pretty hard because P4 is large and complex. So instead, what we want to do here is that we want to define a subset of P4 that is expressive enough to only deal with the match action pipeline, which I'll describe what that includes in a second here. But that we can still target with our Coq representation. So this is a bit of the grammar for how this P4 subset is going to be defined. So we just have a program P that has multiple declarations followed by a control block. And then what a declaration can have is either a header, and the header has fields with their types. We have an action definition specifying the type parameters and a body statement. And then we also have a table definition listing keys, which are at either header fields or expressions and possible actions. The actions here being if we want to send a packet or we want to drop it from the information, or if we just want to hold it. Then we have the control block. So this simply apply for a statement S. Then we have our generic statements for control flow and expressions for simple arithmetic. And so here are two, again, simplified semantics for this subset. So what we have here, we can have a small step operational semantics in which we have a tuple, so we have a sigma and a packet. So then in T action, this shows how the action is going to be executed. So we just look up the action body for body of A, this is typically just going to be a list of assignments. So we just enumerate those assignments, and these are just going to be expressions, and we just evaluate these expressions and then update the packets accordingly. Pretty straightforward there. And then for T apply, this is going to cover the table application. So if the table match picks an action A, we then run that action small step execution. And of course, there's more so for control flow and sequential composition and assignment here for the packet header fields. So there's something important here we have to take into consideration, which is why this subset is actually sound for, quote, normal P4. Again, I'm given P4 code, and then the idea here is that I want to be able to try and make it so whatever code they give me still works within these semantics, but I don't want to overcomplicate my semantics still. So I've just focused here on these core constructs from the match action pipeline. So it's just headers for the field definitions, tables for match, actions for field updates, and the basic control flow. I'm pretty much ignoring any more advanced P4 feature, as well as omitting specialized hardware-bound P4 features as well. Okay. So now we can see how exactly I want to use this small P4 subset. So the idea here now is that I have a network calculus, and this network calculus has proofs, and now I have a language that can actually interact with Coq in some way, because it is separate from P4. So what I now need is some sort of IR in which I can compile this subset of P4 into some Coq representation that can then go through the Coq proofs I did earlier, and then we can actually see if whatever match action pipeline, so this very specific type of algorithm, whether this is correct or not. So here we just replicate the P4 subset structures again, and we define. So now this is how it looks like in Coq for what I call netQIR. And now we can get into the actual semantics of netQIR. So now we can go back and we can start connecting with the network calculus. So here we have flowspec, which is a function that for each netQIR statement, it returns a service curve describing the minimal guaranteed service. The netQIR language ensures statements are safe from this rewriting perspective. And while the flowspec ensures, we can also talk about the timing and throughput guarantees through this definition here. So as an example, we can say that if we can say that for the invoking of an action, that invocation corresponds to 1 millisecond of processing, then we can model that processing delay as a simple beta. The beta of t delayed is going to equal just the max of either 0 or the total amount of time minus the delay 1 millisecond. So this is implemented then in the composition rule. So we have now for the composition of S1 and S2 for flowspec, we have the simulation of the cascade composition in the network calculus. So we say if stage 1 here, so you can see at the top of the slide, so if stage 1 has beta 1 and stage 2 has beta 2, the overall pipeline has then B1 O times B2, connecting the network calculus to this language now. So now that we've unified this flow bounding perspective from the network calculus and this language, the idea here is to show that no matter the arrival function A, we get a departure D satisfying the typical network calculus inequalities for whatever netQIR program we define, for whatever function we write in it. So this is the end-to-end theorem in netQIR. So we have this hypothesis that just means that if P is well-typed in netQIR's type system, then this prevents ill-formed statements. So this can be, for example, writing a bit 16 into a bit 8 field, which is important. If we go back to the bundled protocol versions, they have different sizes for these fields. So it really matters how we want to, it really matters to make sure that we don't end up overflowing the wrong version because of this. So the conclusion has 2 parts here. So we have the first part, so for that, the formula on the second bullet point there, which states that the classical service curve-based performance is guaranteed from the network calculus. and that no unintended packet duplication or corruption is captured in the semantic correctness of the language, which just means that actions and tables don't create new packets from nowhere or miswrite them incorrectly. So yeah, basically in practice, flow spec of P is defined by associating a curve to each statement. So then we can go here to the overall compilation pipeline diagram, in which we parse the P4 subset, we check the types, then we translate each statement to netQRR, aligning the semantics. Then the netQRR code is fed into Coq, and then we apply the proven results. So in this case, it would be just the packet correctness and the network calculus flow bounds. And then if something fails, like a type mismatch, we feed back an error message. So now the important part here is we need some sort of type preserving compilation process to make sure that whatever subset of P4 we have defined, when going into netQIR, it actually preserves. So then what we are mechanizing is essentially the same as what we did not mechanize, which is the P4 code. So here we just have the compilation function, translates each P4 construct to its netQR counterpart. And here we have a couple of things. So we have an action. So for this action, the compiler extracts each assignment from the P4 body and then converts it into one of netQR's sassigned statements. So for example, for parameter types, so for like bit 32, this becomes t-bit of 32 in netQIR. And all these statements are wrapped into a netQR action block with the same name. In this case, it would be the name A, since that's what we have here for an action A. We also have then the table. So for a P4 table listing key fields and possible actions, this is mapped to the S table apply of T. And then the logic is reasoned about in netQRR with our T table, T apply rule I showed earlier. And we also reason about the typing environment in this similar way. Then we have, so then we have the well-typeness preservation here. So so if the P4 program passes the P4 type checker, so this means that there's no mismatch between bit widths, action parameters or whatever between the two bundle protocols, then the resulting netQR program is well typed. And this is essentially to reuse the netQR theorems for packet correctness and flow bounding here. So that gives us that gives us the basics for how netQR works. Then we also have here the some proof mechanisms, but for the sake of time, I'll skip that now and I'll just go to the example here. So this is an example from the original P4 code. I just cut it and then modified it a bit for it to make sense in my subset of P4. So here we just set the egress port and rewrite the MAC address and then decrement the time to live, the TTL. So then, in the SDDTN context, this would be the equivalent of rewriting the bundle protocol version block or setting a priority. And then now we can look here, the compile netQIR plus flow spec version of it after it goes through the pipeline. So you can see the compiler yields the netQR action with the 4 sassigned statements. We attach the identity service curve or the slight shift to each assign, and the inductive Coq proofs then shows that the final packet fields match the intended rewriting for the original minimal service guarantees. So finally, to put it all together then, we have then that for a netQR program that is well typed, and the program must use these correct assignments and references. The flow spec of P assigns the service curve to each statement. So in this case, we have IPv4 forward. So for this function, each field update is effectively has effectively a 0 delay in the abstract model, in the network calculus model. So the total service curve might remain as the identity for the actual implementation of this. So there is no delay here. So from the network calculus, we know that any arrival function A into that pipeline is lower bounded by A star beta forward for whatever given time and the at the output D of t. And then for the Coq proof here, so for the base case, we had that a single SSI modifies exactly one packet field, preserving the rest, so correctness of rewriting is immediate here. We have that flow spec as identity, and then for the inductive step, we just run this on the sequence of statements composed by O times. And yeah, so then to conclude then, we have a combined minimal P4 subset, which just targets this match action pipeline with this specific IR, NICQIR, to ease the verification and to indirectly mechanize this algorithm for converting from a bundle protocol v6 to bundle protocol v7 stores and forwards. So you could have the P4 code separately, just feed it through a pipeline, and then you would know if this specific, the specific functions you called for these bundle protocols is correct or not. So for possible directions here, there's more to do in the terms of the bundle protocol features. As you saw, I'm only giving minimal service curves here, and there's a lot more like handling full bundle protocol fragmentation or custody signaling. There's also obviously expanding for the entirety, or not entirety, but a more broad set for P4 or other languages as well. And obviously, there's also testing it on actual NASA testbeds, which hasn't been done. It's only been compiled, but it hasn't actually been tested with deployed code. And then the renaming, because I named this NetQIR, the Q from Coq, but as Coq is now Rock, then possibly rename it to RockNet or Rocket. And that is it. All right, thank you.
So we're a little bit behind, but we have time for questions if there are any questions. I have one quick one. So in your theorem, maybe a couple slides back, this D, where does anyone, yeah, whatever the theorem's, this one, where does D come from here, right? So A is universally quantified. What is the connection between the departure D and the arrival function? Where does D come from?
So D is just it's not the arrival function, it's just the destination time. So it's just going to be, that's defined over here. Let me find it. Yeah, here. So you're always going to have that the destination is always going to be greater or equal to the arrival time here for showing continuous flow in the network.
So does D depend on the input program, or so D is just a constant? I guess I'm.
Yeah, D is dependent on the input program.
Okay. So
yeah, this was
implicitly hidden maybe in the compilation. Okay, so that makes a lot more sense. Yeah.
Yeah, this was in one of the examples. Sorry, it seems I don't have it on the screen, but this is the example for when you have the corresponding delay for like 1 millisecond, then that would be within the arrival time there. That'd be the delay. So you'd have whatever t minus the total delay.
Yeah. Okay, that makes sense.
Yeah.
So, any other questions? Well, if not, let's thank Jan Paul again. And
all right, thanks.
Break for more coffee or cookies or whatever.
Welcome to the last session of CoqPL or RockPL. Without further ado, this is our first presenter, Prasita. So she will be talking about verifying C programs and synthesis using LLM.
Okay, thanks for the introduction. So I'm Prasita. We are here to talk about Synver towards automated verification of LLM synthesized C programs. This is joint work with my advisor, Ben Delaware from Purdue University. So to start with, the keynote on Wednesday presented an appropriate picture of the present scenario of program synthesis. On one end of the spectrum, you have these deductive synthesizers that produce programs with strong guarantees, but they're not that expressive. And on the other end of the spectrum, you have these LLMs, large language models, which are black boxes, and they would, owing to the large search space, they would always produce a program or a set of programs given a specification. So what we tend to do in this work is we tend to elevate the guarantees of an LLM-generated programs by incorporating a foundational verifier. So we present a general purpose synthesizer in the form of LLMs, which accept a diverse set of specifications ranging from separation logic to API calls. And given the specification, it generates a program, which is then subject to verification. And we use foundational verifiers like Rock or Coq in this case to reason about their correctness. Now, as we said, LLMs have large search space, so it is always going to produce some output. And since we are subjecting it to a diverse set of specification that is expressed in a rich logic, we use foundational verifiers to reason about their guarantees, and there's a significant verification effort needed. There have been works like Suslik and Cobalt. Suslik tackles synthesis of heap manipulating programs, and Cobalt tackles synthesis of API programs, but then they're again standalone synthesizers. They're not as general purpose as we achieve in this work. So the goal of Synver here is to, again, reason about the full functional correctness of programs generated by LLMs, and we do this by incorporating automation inside Coq and with the help of some user assistance. So this verification comes with a set of challenges. This is too good to be true. So given a whole triple PCQ, where C is the program that is synthesized by LLM, we use VST and incorporate some automation on top of it to verify the C program generated. But given the automation, since this is a very rich set of specifications we are dealing with, it can produce a set of unresolved goals. And these unresolved goals can be in the form of either the automation is not strong enough to discharge them, or the program generated is incorrect. So in this work, we tend to eliminate the set of unresolved goals to the minimum by either completely automating the whole proof or minimizing the set of unresolved goals. And we do this by incorporating certain biases in the search space. So let's look at a demo. Oh, OK, I have it. All right, so here it asks us to enter the specification and separation logic. We are trying to append a list. Then the function name followed by the function signature, and then the English description of the function. Then it asks for a couple of input-output examples. This is how our prompt design works. We provide the first one, the second one, and then it asks us to provide the name of the specification file. We provide everything, and we see there's a program that is synthesized, and this is generated by the LLM. Now, if you look at it, we will see that it does indeed generate the correct program for appending to lists. And we see that what we observe in the output, and I will be highlighting you, is that Synver is able to completely automate this proof. So it says that it's successfully verified against this specification. So now let's look at another example where it may not be able to automate it completely. So this is another example which will try to delete the first element of list, of a single linked list if possible. So I'm not going to walk you through all the details. We enter all of them again, and we see that there is a code synthesized, and this code is correct on examination. But it says that it cannot completely automate the proof. It does generate some error files, some side conditions. And we look at the side conditions. We examine the error file. We see that it's unable to resolve an entailment. And this is a single linked list. So on inspection, we see that the two lists on the left and right-hand side need to be equal. And then the user can manually walk through the specification file and look at the partial proof generated. And we see that this is the sub-goal that it failed to automate, and the user will assert and prove the equality of the left and right-hand side list, and then they're going to perform the rewrite, and then entailor is going to take care of it. So this is how we discharge the proof when sub-goals are discharged, not able to automate. So we present the outline. So Sinver is a general purpose synthesizer for C programs. We generate easily verifiable code through prompt design. We propose a verifier called SepAuto, which is an LTAC on top of VST to automate proofs that are generated in this fashion. For programs generated in this fashion, we conclude with the experimental setup and results. So now we present the workflow of Sinver. So there's the LLM, the specification, and the biases. It will generate a program which is subject to syntax and bias check. Until the checks are done, it's going to do a to and fro with the LLM. Once it is syntax checked and bias checked, that program is then fed to SepAuto, which then either completely automatically proves the goal or involves the proxy, which is user here, to either discharge the proof, or it's unable to discharge the proof, which means the program is incorrect, and then the user appropriately reprompts the LLM. So now, natural question is, why do we need to incorporate these biases, and what are they? So our goal here is to generate programs that are easier to verify, easier to automated verification, so which is why we incorporate these biases. And what we observe is that we would not want to infer novel specification and then verifying them, because inferring novel specification is non-trivial, and that requires extra verification on top of it. So if we can somehow eliminate this with alternatives, that would be a good option for programs in this space. So what we say is that we say no to loops and yes to recursion, and we give it a set of novel helper functions, and we only ask to use those helper functions, to not infer any novel helper function. So if take a look at the workflow, this is the first part where, let's say it passes the syntax check. So in the LLM, we say that recursion please and only call function given. And if it doesn't follow the biases, we reject them and keep reprompting until the program is generated in the correct shape. So here we meet our objective of no specification inference. Now, the second part is this is not related to the biases, but we tend to write specifications that are automation friendly. Now, VST comes with a set of very advanced tactics and algorithms. One of them is list solve, wherein we observe that writing specification with predicates like for all 2, and instead of like inlining them like writing a spec for ascending order, writing specifications using predicate and expressing the relation of pairwise elements would help automate it better. So we tend to write specifications that are automation friendly. Now, once the biases are checked, we feed the program to SepAuto for verification. So now I'm going to do a walkthrough of how SepAuto works. So SepAuto works in a similar fashion to VST, that is, it does forward symbolic execution. So this is the part that I want to focus on, where you have generated a program that is bias correct and syntax correct. So once what SepAuto is equipped with is a set of data structure, hint lemmas, and it does shape analysis. So it uses the VST Floyd tactic forward to keep doing forward symbolic execution until it's stuck at a state. And then it examines the stuck state. The state can be a hot triple or a non-hot triple, and it does certain automation tactics based on the shape of the goal. So let's look at certain cases. So the first step is the if statements. If there is an if then else statement, which is followed by another statement, so here D follows the entire if then else block. Here, VST uses a tactic called forward if to drive the symbolic execution forward. But if there is a statement following the if then else, it would require a joint post condition. A joint post condition is nothing but the specification of the two branches, but we don't want to do specification inference. So what we do is we transform the goal, and by pushing E into both the then and the else block. So if once we transform the program, forward if is then able to automatically discharge the next step without requiring specification. So in this way, by transforming the goal, we avoid inferring specifications. The next part is function calls. Now, function calls are really important in our paradigm because we deal with recursion and we also deal with API calls. VST has a tactic here, forward call, to drive the proof, which requires parameters of the function call. Now, this is quite non-trivial, and it often fails to infer the correct set of parameters. So we do have a tactic for parameter inference. I'm not going to go into the details of the tactic, but if it is inferring correctly, it's not guaranteed to infer correctly. If it infers correctly, then we move forward. Otherwise, the user is involved to provide the parameters and make progress. But in spite of all of this, querying the relevant proofs, hint lemmas, it may still fail to make progress. In that case, also, we do need assistance from the user, where they can either resolve the goal or may just reject the program, telling the LLM that this is the incorrect program. So for non-hot triples as well, we perform a similar kind of automation structure. So it looks at the shape of the goal. It can be an entailment, inequality, etc., and it would fire the respective tactics. So VST is already equipped with a rich set of tactics like entailer for entailment, LIA, listsolve, etc. If it's discharging the proof, well and good. Otherwise, it looks at its hint lemmas, tries to discharge the goal. If it can't, then again, the user is involved. So now we've presented the outline of what SynVer looks like. So now we go to the experimental setup and present results of what it can actually do. Okay. So here in the experimental setup, we have a benchmark of 50 programs, and we split across basic, which comprises of arrays and basic variables, separation logic, which comprises of heap manipulating programs and API calls. We don't propose this benchmark. These are a set of programs that are borrowed from the synthesis community. We do support multiple types for the programs. So all the programs are supported with integer types. We also have support for strings and very limited support for double to automate the proofs. We use GPT-4o as the LLM, and it is prompted with the components as we described, along with the biases. So now in our results, we see that GPT was able to produce the correct code for almost all the programs but one. And it did incorrectly generate the code for one case, which I'm going to talk about, which is this generate skewed BST. So what it says is, given the list of n keys, generate a skewed BST. And given the description of the prompt, it's unable to parse. So what the user comes in and says is, I'm giving you the definition of what a skewed BST is. In spite of giving the definition, it still fails to produce the correct code. Then the user says that you have to sort the array in ascending order and then insert the keys one by one. So basically, we give the whole algorithm, and then it's able to generate the correct program in this case. Now coming to the results, so SepAuto is able to, the automation results, is able to mostly automatically verify the set of benchmarks, but it does generate side condition, and it's not complete. The side conditions, as we highlighted a couple of them, and we'll be looking at some examples as well. First thought and BST min node, like first thought, the specification has nested quantifiers, which is difficult to automate, and BST min node requires the magic wand of the separating implication operator, which is also difficult to automate. Now we evaluate our results by posing certain research questions. The first question is about the biases. So remember, we talked about the biases that we don't want loops, we want recursion, and we don't want it to synthesize novel helper functions. So what we want to ask is, if we don't provide the biases in the prompt, what kind of programs will it generate? Will it generate automation-friendly programs or not? So we reran experiments, and what we found out was, of the 26 programs that required recursion, 24 of them were generated with loops. So it naturally tends to emit programs with loops and not recursion. For helper functions, they typically don't tend to synthesize novel helpers, but for one of the examples, isEven, we found that it synthesized a function called isOdd and tried to verify it, which was not present in the set of function calls given. Now, I would like to walk through some of the cases where SepAuto may fail. So this is one case where it fails. So basically, there are two indices, IND and VRET. It fails to infer the relation between IND and VRET, and we need to destruct it with the appropriate inequality. Since it fails to realize this, it gives up, and then the user destructs it. We have multiple sub-goals, which is then automated by SepAuto using the hint lemma sublist split by taking into account this hypothesis. Then the second one, as we saw in the demo, is we have an entailment on the left and right side. It's a singly linked list that ends at null. It's not a segment, and it starts at the same address, so which means that both left and right-hand side, they represent the same list, but it is unable to pose and prove this premise. So in this case also, it gives up and the user proves it, as we saw. Then the third case, as I talked about, automation is supported. It's very limited for the magic wand operator, and it does need user assistance in this case. Now we extend this research question by analyzing the failure mode of SepAuto versus other verifiers. We do comparison with Framacy, VeryFast, and RefineC. Now Framacy, it's very good for the basic category of programs, but when programs require dynamic memory allocation or when it involves separation logic conjuncts, it requires a lot of annotation burden, which is very difficult to infer. VeryFast is, again, more expressive than Framacy, but it's, again, automated. So in VeryFast, for example, there's a program that is synthesized correctly. It's very fast, but you may need to insert annotations in between. And if you don't insert it correctly, this is the correct program. It would say the error message in the verbose mode is that it's unable to verify the correct post condition and alongside the SMT queries. And as per my experience, it doesn't give a concrete set of goals as to what went wrong. And I can infer whether I have to write a lemma or annotation or what. Refine C, on the other hand, is both automated and foundational, so it's very expressive. It has good automation support for the WAND operator as well. But along with the annotated specification, it does require support for certain hint lemmas or tactics for the proofs to go through. So do a fair evaluation. We commented out the helper tactics if you're not able to synthesize, but we found out that in this case, it does. If it's not able to do the whole proof, it generates the unresolved goals. And these unresolved goals are of the nature which SEP Auto can discharge. So what we found out was SEP Auto's automation can be fed into other foundational verifiers like Refine C to discharge their unresolved subgoals. So, so the last question we pose is, do the components of the prompt matter? So we saw that the prompt has a bunch of components. So how much does each component of the prompt contribute to generating the correct program and the desired program? So the first rank is the biases. We saw that if we don't give the biases, it would tend to emit programs with loops, mostly. And then the English description, then followed by the meaningful function name, which is also in English. Then the formal specification, and input-output examples are basically don't cares. We didn't find them affecting. So we evaluate this by doing certain evaluation studies of the prompts. So this is a specification which is saying that you want to return another list, which is using the filter function. So you don't want to change the list. You want to create another list and return the head of the list. And over here, we don't give any English description. There's a mathematical description and the biases. So what we see is there's a program synthesized, but it's not quite correct. It's modifying the list. So this led us to conclude that maybe LLMs don't have a good understanding of the separation conjunction operators. And on running our benchmarks, we found out that only 12 out of 23 programs in the separation logic benchmarks were generated correctly. To further solidify our claims, the next evaluation that we conducted was we gave a proper English, a very descriptive name, but we didn't give the natural language specification of the same function. And it did generate the correct program. And the final result was it was able to verify 20, which is an improvement from 12 in the separation logic constructs. So to conclude, LLMs with foundational verifiers giving guarantees can be used as a general purpose synthesizer. LLMs have a large search space, and since C is a very mainstream language, it is well trained on C, so it gives us correct programs following the biases. It does respond positively to biases, and the automation is well suited. SEP Auto is, again, not complete. It can generate a set of unresolved goals where we need user assistance at the moment. But yes, it is very possible that there might have been a data leak, because of which we observed that it was generating correct programs for almost all of the programs in one try. So in the current state right now, what we have in this framework is, with some automation on top of Coq and user assistance, we are able to reason about full functional correctness for the programs that are generated correctly. What we want to achieve is that right now, with the automation support and no user support, it's able to automate a bunch of the proofs, but it's not quite up there. So what we want to do is minimize the assistance of user in the loop for now. And what we are immediately looking at is giving the unresolved goals to LLM and examining how much they can discharge the proofs and how much we can do by just having LLMs discharge the whole thing instead of having users. We want to minimize user involvement, and also we are looking into automating the WAND operator and working on other automation aspects where SEP Auto fails. Okay, so this is the end of my talk, and with that, I'll be happy to take questions. Thank you.
We have time for a few questions. Yes?
Really amazing talk. I have a question about the prompting part. So I'm curious to know how sensitive it is to prompts, and is there any specific structure or way that you have to prompt to get the right solution or to guide the LLM towards?
Yeah, good question. So what we found out, as I said, it's very sensitive to the natural language description. So if that is not correct, we found that it's not quite generating the correct code. So the English description needs to be absolutely on point. The input-output examples we found out where it was not affecting, but the proper English description of the specification needs to be there along with the biases which are also described in English.
So what do you mean by proper English description?
So you eliminate ambiguity as much as possible. That's what,
okay.
Yeah.
Okay.
So when I'm talking about filtering a list, I would say that you make a copy and return the pointer to that list and not, sort of modify that list, something like that.
Okay, in a way like you're kind of giving informal description.
Right. Yeah.
Thank you.
We have time for one more question.
This is too good to be true. So I want to know, like, how were the specifications provided? Were they in natural language or some formal language?
Yeah, so they were both formal specifications were provided as well as natural language specifications were provided. So both of them
So
were provided.
both of them, you should have both of them, right?
In the prompt, we have both of them, but in our ablations, we kind of concluded that it is more like it listens to more of the English description to generate the correct program.
Is the recursion like multifunction, or a function can only calls itself?
Right now, it is only calling itself. Right now, our benchmarks don't have mutually recursive call, if that's what you're asking. Our benchmarks don't have that, but I believe it can support it. But yeah, our benchmarks don't have that. Yeah.
And one very short question. If you don't like loops and like recursion, why not a simpler, I don't know, functional language? Why C? Is it because
C is a mainstream language. We want to assess the ability of LLMs to generate in a mainstream language like C and argue the full functional correctness of it, rather than that's.
Thank you.
Okay. I guess we can ask one more quick question. You want to ask a question, right?
Just a quick clarification.
Yeah, and maybe you can ask while setting up your talk.
So you mentioned that data leakage might affect the results, and I don't know what data leakage is, so if you could explain.
Yeah, so it might have been possible that the LLM has already seen that program, so it was generating it correctly in one shot. Thank you.
Our next speaker will be presenting remotely. Do we have slides? Okay, our next speaker will be Christine, and the talk will be about mining Coq proof patterns. Christine, you can start your presentation.
Hello? Hello?
Oh, really? Hello, can you hear me?
Yes, can you hear me?
Yes. Yeah, you can go ahead and start. Thank you.
Okay. Can hear myself, but that's okay. Okay. Yeah, thanks everyone who's still here, I guess, for the last two remote talks. So this talk is about some project that we want to do, and it would be good to get the CoQ community's input on the project. So our motivation is that proof maintenance is challenging, and proofs break a lot over time. They're hard to write in the first place, and when tactics or underlying proof libraries change, then proofs tend to break. And it takes a significant amount of effort to maintain these proofs. And I think this project is mainly trying to investigate how we can automate proof repair. And so usually people, especially who write ROC or CoQ proofs, tend to write tactical proofs. And tactical proofs tend to be fragile because small changes require major refactoring of the proofs. Like, for example, if one tactic fails or fails to solve what goals that it solved before, then it's kind of hard to detect where the breakage is, and also kind of hard to fix it. So the goal of this project is to use techniques that have been used in software maintenance to do proof repair, and in particular in program repair. So people in software engineering have faced this quite a lot, and we're trying to use similar techniques and adapt these techniques to proof repair. And it would be good to get some input on what we're planning to do and if people have advice. So proof maintenance is not something new. So there have been mathematical libraries formalized in Mizar since the 80s, and people have been trying to automatically maintain proofs since the 90s. But even until this day and age, a lot of the responsibility for proof repair falls on the original authors of the proofs. And if these authors are no longer maintaining the proofs or no longer active, then a lot of proofs just become break and become hard to repair over the years. So so automated program repair has seen a lot of success in industry, and they use learning and mining techniques for code maintenance. And there have been some recent developments in proof repair world. So for example, there has been a recent ROC dataset that was published to study proof of evolution. And basically, they have several proofs over several versions of CoQ. And there is some initial work on using large language models to repair proofs as well. So where do challenges lie? So first of all, there are various, types of proofs. There are tactical proofs and there are more declarative proofs. And declarative proofs tend to be a bit more robust because they have an explicit structure that aids with the maintenance. And by declarative proofs, I mean proofs where you declare where you're proving everywhere. So you have a lot of sub-goals or a lot of lemmas with very small proof scripts and so on. Well, one thing that is extremely robust, but kind of painful to write is proof terms. So I have some ROC proofs from back in whenever I learned how to do theorem proving in maybe 2009 that still work on every version of ROC that I've tried them on because they are just proof terms, explicit proof terms. But these were proofs about some logical transformations, and proofs for any sort of verification or verification of programs would be too painful to write this way. So there doesn't seem to be any sort of well-established maintenance strategies or advice about how to even write proofs that are easy to maintain. Maybe there are some, but they're not that widely spread, I guess. And people don't often consider that as a main priority. At least I don't consider that as a main priority when I'm first trying to prove something. So one question also that we have is how can we identify robust proof patterns? So what we want to do is we want to mine proof repair patterns from data that is collected, and we want to learn some repair templates. So how people repaired previous proofs, and also what sort of proofs broke in the past over time. And maybe that would help us identify what are robust proof patterns that people use. So what we want to do is first data collection, and then mining, and then proof repair. So with data collection, we want to use Coq datasets to identify the historical patterns of breakage and repair. And we want to analyze these patterns. And in terms of mining, we'd have to convert the proof scripts into some sort of abstract syntax tree. This is what people do in program repair world. So they take a program, convert it to an AST, and then they use something called tree differencing to analyze the changes in the program. And we could do the same with proofs because they're programs. But one thing that we get in proof world that people don't have the privilege of in program world is that we could, after we generate the templates and instantiate the templates to get proof repair candidates, we could validate using Coq whether these repairs have actually worked and the new proof actually works. And if the new proof doesn't work, we could iteratively refine our templates until a correct repair happens and our proof is restored. So yeah, in terms of data collection, well, yeah, there's a recent data set that we could rely on that contains proof changes across Coq versions. But one thing that we'd like to ask you is whether you are aware of other sources that we should consider. So other big sources of Coq proofs, because there seems to be, like with Isabel, there's the Archive of Formal Proofs. With Coq, I'm not sure. There's MathComp. There's this data set which may or may not contain MathComp. I'm not sure if there are other sources that we should be looking into in terms of data collection. And then we want to analyze the proof evolution and identify failure points and categorize proofs as either fragile or robust. And for the second phase, we want to convert the proofs to some sort of ASTs. Use tree differencing techniques. So these ASTs will not be as detailed as the AST that Coq uses to check the proofs, but it would be sufficient to do tree differencing on it. And we want to extract common repair patterns. Now, for the third phase, we want to generate candidates, validate them using Coq, and iteratively improve our repair. And one practical advantage of that is it would obviously reduce proof engineering, and therefore we're hoping that it would keep more proofs up to date. And in terms of theoretical interest, it would help us also investigate somewhat practical relationship between proof and program repair, or like what works and what needs adaptation. And in terms of community benefit, it would be good to learn using existing data what sort of proof styles are robust, and promote modular proof structures and showing how these modular structures result in robust proofs. And it would be nice it would be great if we could provide a guide on how to write maintainable proofs. And and it would be great if we could have a proof automated repair framework out of this and guidelines for maintainable proofs. And it would be good to get your feedback before we actually go through this and understand what are pain points that you have when you're repairing your proofs by hand. And if you have any advice for us on how we can refine our proposed approach, that would be great. And also data sources. So data sources for Coq proofs other than the ones we mentioned. Yeah, and if you want to collaborate on the project, we're open for collaborations from this community. So please reach out. It's great to work with others. So yeah, that's mostly it. After we're done with this, we'd like to evaluate it on large proof repos. So yeah, again, if you have other repos than the ones we're considering, please let us know. So yeah, just to conclude, proof maintenance is quite challenging. Software engineering techniques have been quite successful in industry for automated program repair, and they offer promising solutions. It would be good to see how we can adapt these solutions and use them now that we've scaled up verification to enormous libraries and repositories of proofs. And that may help us improve or automate some of our proof repair and keep our libraries up to date. And yeah, finally, we welcome your feedback and collaboration. Thank you for listening. I'm not sure if anyone has questions or comments. I don't currently hear you.
Thank you, Kristen. Any questions from the audience? Yes.
Hello?
Hi. Okay, mic works great. So, Christine, it's Marco Doco. We've met before. I have a silly question that's not immediately answering any of your questions, but it's, you said proof terms are robust. So I was thinking, how bad would it be if you have a developer that dropped out and you have a very proof that's not maintainable anymore? To go back to the version of the prover that where it worked and just get the proof term and remember that, would that kind of make things, well, not maintainable, it's no longer readable, but fine, the proof term stands and is supposed to be robust? Is that a viable approach?
Interesting idea. I'm not sure how, I'm not really a Coq developer, so I'm not sure how big the proof term would be in Coq. In Isabelle, for example, that would not be possible because they throw away parts of the proof terms. They're enormous. They can't even store them, so they throw them away once they're checked. I know in Coq you can theoretically extract a proof term. For a big proof development, it might be gigabytes or terabytes of amounts of term. I haven't tried proof term extraction from a in Coq. Maybe someone in the audience who's a Coq developer or who has used that feature could tell us if it's viable. But yeah, converting it to a proof term and then trying to reduce the proof term would be one way to try to try to at least do the repair on the proof term or something like that. If the size, yeah. So I guess my answer is I'm not sure. I'm not sure if we'd run into size issues and practicality issues with big developments or not. If not, that would be great. It sounds like a good idea.
It's Enrico speaking. I wanted to answer your question about the size of proof terms. Well, they are big, but not that big. I think that the proof terms for the Other theorem were a few megabytes. So it's viable.
For a big theory file, or
yeah, the Other theorem was 100 files.
Okay.
I mean, no, the proof terms are not that big, and they are saved on disk. When you compile a Coq file, you get a VO, and the VO contains.
Yeah.
So they clearly fit your disk. That's not.
So I wonder if the proof term contains just cuts, so whether it contains names to lemmas elsewhere that also have proof terms, or whether it's an unfolded everything back to no definitions and lemmas kind of proof term? Because then it would be enormous, right?
No, they are not unfolded. You get
So if they're not unfolded, then the problem is not solved, because if any of the underlying lemmas change or the definitions change, then sure, we have a proof term that's linking to something, but that something is something else now. Do you see the... It may solve part of the problem of like tactics changing, but it doesn't change. But the proof will still break. The proof term will still break on the new version if the underlying lemmas and theorems are now different. Does that?
Do you have some idea of the things you expect to break? My experience is for larger developments, the things that break are fairly intricate. So you'll have changes, subtle changes in the way the simplification engines will unfold or not unfold terms. You have subtle changes in the way unification works. The more problematic are efficiency breaks. So
Sorry, more
so
problematic
your
are?
proof is still valid, but it just doesn't type check.
Oh.
Just takes forever, or just instead of taking 20 seconds, it will take 20 minutes or 20 hours.
Yeah. Okay. So when I say break, I mean actually break. So there's also the proofs that may take way longer, and it would be good to simplify these. But even if we just focus on breakage, I'm not entirely sure, but from experience, it's usually either underlying tactics changing or something getting added, and now things, the tactics behaving. So either tactics behaving differently, or like an underlying lemma being renamed or changed slightly, that would break things that rely on it. So underlying libraries changing. And often when we fix the, like when you do one fix for something, it will work for a lot of other things. Because like if you're relying on a lemma in several places and it changes or gets renamed and you fix that, then you can do the fix in various places. So that sort of stuff seems a bit, at least that sort of stuff seems like low-hanging fruit. And I think for us, the idea is even if you don't get 100% proof, automatic proof repair, this sort of stuff that's time-consuming and not too difficult, maybe for a machine to do, would be nice to fix. And if we get like 80% of the breakages fixed automatically and you have to do 20% by hand, that would still be good.
I don't think we have time for more questions, but let's thank Kristen again.
Thanks, everyone.
Okay, thank you. Okay, the next speaker will be...
Hi.
Hello. The next speaker will be Qiu Yi. He will be talking about formalizing quantum stabilizer code. And I believe this will be our last talk. And yeah, let's take it away.
Thank you. Yeah. Good afternoon. I'm really excited to be here to share our works. We are a team of 3 researchers from the University of Melbourne, and I'm Qiu Yi. I will present on behalf of my co-authors Udaya and Christine. And this work is regarding applying formal methods in quantum computing or quantum programs. So let me first introduce some concepts in quantum computing that has profound effects on this project. The first thing we want to discuss is the quantum bits or qubits. the principle. This is a principle for quantum computing. They say the quantum bit might be in a superposition of both 0 and 1. This is really different from classical electronic bits. So conventionally, we can write it as this expression, and we can visualize it as this sphere. So you can imagine a quantum bit to be located or to be survived on the surface of this sphere. And when we measure it, it will collapse on the z-axis. So it will be either 0 or either 1 by the probability of the state. So another principles or another properties of quantum computing is called the entanglement. So it says when several qubits form a joint state, if I modifying one qubit, they will immediately affect other qubits. So we can consider this quantum state, which calls the Bell state. So this state has a one half probability to be in 0, 0, and another one half to be in 1, 1. But it has a unique probability that if we know the first qubit to be 0, we know immediately the second qubit is also 0, no matter how far the two qubits located in physically. So this is really important in applying formal methods or quantum programs. So why we are trying to do this? Why we are going to apply formal methods in quantum computing? So our first observation is that quantum programs are really hard to test. So we talk about superposition. This is a principle that will cause this non-deterministic probabilistic output of programs. So even for probabilistic classical programs, there is a really hard difficulty to apply any tests to it. You need to collect the distribution of that program, distribution of the output of the program, and to think if the distribution matches what I want. So this is really hard to test. And we also talk about the entanglement. This will have the effect that if an error happens, it might spread across all qubits or entangled qubits. So you can so it will be really hard for someone to locate the source of the error. And we also know that the computation resource of quantum computers is scarce and expensive. So for a financial or economic point of view, we want to verify it, and we want to make sure the quantum programs is correct, right? So our first observation is that quantum computing is formalizing first principle. So this is a common problem in classical settings, that when you try to verify a programs, you will find the program language is not formalized, or we can say that it does not have a formal semantics. But this is not the case for quantum computing, because the whole area of quantum computing is inherently developed in formal mathematical frameworks. They describe the computation by a denotational semantics of in a vector space. So we can see that every quantum operation has a formal denotational semantics, so we can easily translate the programs into a mathematical expression, and we can verify it. So we have our work is built on the recent advancement in this area, and we would like to express our sincere gratitude for these excellent contributions. There are two main approaches in this area. The first one is a low-level verification, which focuses on the quantum circuits. The quantum circuits, like the classical electronic circuit, is a computational model to describe the low-level physical allocations of the quantum gates. So they are square and ZX calculus. They are really great work for us to do our works. And there are also high-level verification. They directly focuses on quantum algorithms, and they usually involve classical subroutines to make a more complex programs. There are also significant works like quantum Hall logic and CoqQ. So our work will be based on the low-level side, but we will be really great to see both area to advance in the near future. So let's give a really simple example. We can swap two single qubit quantum state by this program. This program is picked on the left in quantum state in quantum circuit. So we have two quantum states as input psi and phi, and after we place after we go through 3 quantum gates, they will swap their positions to be phi and psi. So we can write down the specification as we want to require phi and psi and phi, and we ensure the output to be phi and psi. Right, so we can define the programs in here. We use Squire to define this program. We want to swap these two we want to swap these two quantum states, and we write down the program in the first line, the definition, and we declare a theorem to say this program is correct. So by correctness, we mean that if we evaluate any input quantum states on this program, we will reverse the inputs. And we also have a proof scripts. Here we use Squire or the quantum leap provided alongside the Squire, which has some rewrite databases and some automation scripts to build these proof scripts. So we prove that the quantum program has our wanted properties. So what we are trying to do is we want to verify the quantum error correction code. So they are a specialized, or they are a family of quantum programs. They are designed to ensure reliable quantum computing. So why we are going to do this is because quantum errors are really a hot topic now in quantum computing research, because current quantum computers usually have a high error rate. So, and quantum errors are richer than classical errors. So in classical settings, you will often observe a bit flip, but in quantum setting, you will observe other kind of errors that you need to detect, and you want to correct it. So this kind of program is not easy to build, but we have this quantum error correction code, or QECC. It just encodes k quantum states into a larger space of n qubit state. So we call it this encoder to be this program, the quantum error correction code QECC. So before encoding, the original k qubit state is susceptible to certain errors, but after this encoder, the encoded state is capable of tolerating certain errors by using more redundant qubits, right? So this is a really simple QECC, the 3 qubit B-flip error. It used 2 redundant qubits as shown in this quantum circuit. The lower 2 qubits are redundant qubits, and the first qubit is a wanted state. We want to encode it, and we encoded this single qubit state at the output of the circuit on the right. So what it can do, the receiver, if I receive the state, I can detect and correct a single qubit B-flip error. So this is a really easy example, but in realistic, or if we want to achieve some real useful quantum computers, we need to have a QECC with a bigger size, and it can detect more errors. So they will be pretty complex. So why we are going to do this? Because why we want to verify QECC is that they are the forefront of quantum computing research, because everyone is talking about how can we achieve a fault-tolerant quantum computing. So, and they are also non-trivial in complexity. So they are really great candidates to examine how formal methods can go in quantum computing area. There is a most general way of verifying QECCs, and we also talk about this because if you open any textbook of quantum computing, you will see this interpretation of density matrix semantics. They will translate any quantum, you can generally translate any, interpret any quantum programs by this density matrix semantics, and you will get this denotational semantics, and you can verify the any properties you want. So it generally said any n-qubit quantum states can be interpreted as a density matrix operator. So it will be in, so if you want to interpret a n-qubit quantum programs, you need to interpret in the 2 to the power of n dimensional complex vector space, or people call it the Hilbert space. So there are some, apparently there is some scalability issues with it. The primary one is that the dimension of the vector space grows exponentially. So when I put it in Coq, you will eat a lot of memory, right? So, and for QECC, if you want to verify full correctness, you need to try every you need to enumerate every combination of correctable errors by both type and position of errors. So when I try to do this on a small scale error correction code, it will take a lot of time for me to write the proof script and write the enumeration. So our observation is that the density matrix semantics cannot scale well on large-scale QECC programs. So we want to find another more efficient way, or we want to use some algebraic approaches to simplify the verification. And we found the idea from the traditional pen and paper proofs. They prove the properties of, or they just show the properties of QECC by the stabilizer formalism. So it is a mathematical algebraic structure that he used group structures to describe QECCs. So the group structure called the stabilizer group. Stabilizer group is a group that it can stabilize its correct states. By stabilizes, it means it just don't change the correct states. After applying the operations, the state does not change. And it has a unique property that it can detect error states. So after applying the stabilizer, we can detect whether the state is in correct code space or in the error code space. So it can be used to verify or derive important properties of QECCs, like what errors it can detect it and how many errors can be corrected and what's the logical operator on it. And the rationale for it is that it doesn't need to verify the program or reason about the program in a 2 to the power of n dimensional space. So we believe it is more efficient, and it can directly derive many important properties. So we believe it can have a richer description of program properties. And this is still a work in progress. So we would share some recent advancement or progress of this project. So our question mainly is just, can we use the stabilizer formalism to efficiently verify QECCs, the error correction codes? So this have two folds of this goal. The first one is we want to formalize the stabilizer group and its underlying mathematical structures and properties. And secondly, we use our stabilizer group formalism to verify some instances of QECCs. And why we choose Coq? So Coq is a really great tool for this purpose, and we would like to discuss more about this. Coq is shown to be expressive enough for specifying quantum computing process. So like previous work like Squire and CoqQ, they both choose Coq to do to formalize quantum computing, and we work on the Squire. So Coq is a really ideal tool for us to do this work. The secondly is that Coq has a rich ecosystem for mathematical objects, which our works will rely heavily on, like the mathematical component and quantum leap. Quantum leap is published alongside the Squire, which is a mathematical library for quantum computing. So this is our working plan. As I mentioned, is still a work in progress. So we want to formalize the stabilizer group, and we also want to verify QECCs using our stabilizer formalism, and step by steps from the small scale to a larger scale. Finally, we want to achieve the generalized stabilizer encoding program. And what we have done, I'm very proud to share this progress, is that We have formalized construction of n-qubit polygroup, and we have proved some interesting properties of the stabilizer groups, particularly mathematically with eigenvalues. And we have verified the 4-qubit stabilizer code by the density matrix semantics. And by doing so, we find we need to use a more efficient way. This is the motivation of our research. And our research we supposed to have some contributions. The first one, apparently, we want to provide some insights to verifying QECCs, the spatial programs. And we also, by doing so, we also want to investigate the general question like how to apply formal methods on quantum software. What's the best tool, and what's the best formalization and the interpretation? And our formalism of polygroup and stabilizer theory, we believe it can also be reused in other verification tasks. For example, like in quantum key distribution protocol. And thank you for listening. This is our work, and we would like to hear from you. How do you think about this research, and how do you think about applying formal methods in quantum computing? Thank you. Oh. Is there anyone want to
All right, I have a question. So,
yeah, thank you.
So, what is the expressivity of this approach of using, stabilizer group to formalize or verify QECC? So my question is more like, are there problems that you cannot prove, using this stabilizer group?
Yeah, that's a great question, because there are some stabilizer code that cannot be described by stabilizer code. This is yeah, so there might be some mathematically there exists some QECCs that you can't describe through the stabilizer formalism, but we believe that in experiments or in academia, people tend to use this use the stabilizer group as a means to build their QECC and to build the real experiment. Yeah, thank you. Is there other question? Thank you.
Okay, thank you, Chui.
Yeah, thank you.
Thank you. I think we should thank our organizer of CoqPL. And do you want to say a few words?
We should also thank our student volunteers.
Oh, right, yeah.
Job of helping